Welcome. We are going to start off our next session. My name is Maxwell Zeff. I'm a writer with Wired, and I'll be introducing some of our panelists today. But to start, everyone's going to give a short keynote talk. The first is none other than Dawn Song. She's a professor at UC Berkeley, the co-director of Berkeley RDI, and most recently, VP of AI research at Meta Superintelligence Labs. So everyone please give a round of applause for Dawn.
Thank you. Hi, everyone. I hope everyone has enjoyed the morning session, and I'm going to kick off the afternoon session. Thanks, everyone, for being here. Today, I will talk about towards building safe and secure agentic AI. So, year 2025 was termed the year of agents, and this year, we continue to see further explosive growth of agents. And on one hand, we want to continue to enjoy the great benefits brought by these frontier AI capabilities and agentic AI. On the other hand, we also need to pay attention to a broad spectrum of different types of AI risks. And also, in particular, I want to stress that as we deploy AI in the real world, it's important to consider the presence of attackers for a number of reasons. First, history has shown that attackers always follow the footsteps of new technology development, or sometimes even lead it. And also this time, the stake is even higher with AI. As AI controls more and more systems, attackers will have higher and higher incentives to compromise them. And also as AI becomes more and more capable, the consequence of misuse by attackers will also become more and more severe. And hence, it's really important to consider agentic AI in the adversarial setting. And in particular, the overall goal we are trying to achieve here is to advance safe and secure AI innovation to ensure its potential benefits are responsibly realized and widely shared. In order to achieve this goal, we need to develop different types of technical and also social-technical solutions to build safe and secure agentic AI. And in particular, this is a large domain, and we need to actually divide the problems into different categories. So the first part I will talk about is on building secure agentic AI to protect our agentic AI systems from malicious attacks from attackers. And second, I will talk about how we can then, on the other side, mitigate misuse. In particular, as agentic AI capabilities continue to increase, we need to be able to mitigate misuse by attackers. And in particular, I will focus on the impact of frontier AI in the landscape of cybersecurity. So first, let's talk about building secure agentic AI. Agentic AI systems, they can be very powerful and very dynamic. These systems, they use, for example, large language models for reasoning, planning, and figuring out what actions to take, use different tools and so on, and then they allow agents to interact with the environment, to perceive from the environment, and also take actions in the environment. And when we talk about safety and security of agentic AI systems, this actually is much more complex when in the past we only talked about AI safety and security at the model level itself. At the model level, you give it an input, a prompt, you get an output. But with the agentic AI systems, the agents can take rich actions, can have a lot of privileges, and the consequences of attack and misbehaviors can be much more severe. So to learn more information about AI safety and security at the model level, I encourage you to watch my iClear keynote last year. But given the interest of time, for the rest of this talk, I will focus on safety and security issues of agentic AI at the overall agentic AI system level. When we talk about agentic AI, we are not talking about just one single type of agents. Actually, there is a broad design space. In our recent paper overviewing the attack and defense landscape of agentic AI systems, we also outline the overall design space of agentic AI along multiple dimensions as listed here. And the point I want to emphasize here is that along each dimension, as we increase the agent flexibility along each of these dimensions, including the input trust level, the to-use workflow, and so on for the agents, we are also simultaneously increasing the attack surface. And overall, again, in our overview paper, overviewing the whole landscape of attack and defense space for agentic AI, we also identify diverse attack factors and the different types of security risks in the agentic AI space. And you can check out the paper for more details. And this also is not just theoretical. In fact, together with the rise of agentic AI, we're also seeing real-world attacks on agents that's rising fast. For example, Claw Hub for OpenClaw already had a significant fraction of its skills that are actually malicious skills, and we see actually a number of real-world incidents attacks on agents, and it's rising fast. And hence, what I want to emphasize here is that as we increase in agent capability, autonomy, and the set of privileges that agents have, it's absolutely critical that we need to have stronger security guarantees and to ensure a set of different types of security goals, including confidentiality, integrity, availability, and also agentic contextual security and privacy to ensure that agents' actions are aligned with users' intent. In order to achieve this, we need to develop new solutions for building secure agentic AI systems. And here I will talk about two technologies for two main stages of the agentic AI system development lifecycle. The first one is on evaluation and risk assessment, and the second one is on defenses. So in order to build secure agentic AI systems, we first need to be able to do rigorous evaluation and risk assessment so that we can actually understand the different types of risks and different potential attacks on any given agentic AI systems. So my group and with collaborators, we have had long journeys in this direction, and we have been among the earliest to develop, for example, the first comprehensive evaluation framework for the trustworthiness of large language models, for multi-model models, for video models, and also for overall agentic systems. And many of these papers have won Best Paper Awards and so on. And here also is an overview of how we actually think about the overall design space of automatic red teaming for agentic AI. For automatic red teaming for agentic AI, essentially we can think about the system as an optimization loop for automatic attack generation, where we can have these generators that uses different algorithms, including machine learning models and so on, to automatically generate attack candidates. And then these attack candidates are then launched in the environments where the agent is interacting, and then getting feedback, and then the feedback can be used then further to update essentially the generator for these attack candidates. And this can be essentially an automatic feedback loop using different methods to optimize, to generate more effective attack candidates. So the different algorithms for this automatic optimization loop can include, for example, search-based, and also, for example, evolution algorithms, genetic algorithms, and also gradient-based, and also, for example, reinforcement learning-based, and so on. And also this overall automatic red teaming framework can be agentic itself. So essentially, we can build this automatic red teaming agents to actually do automatic red teaming on a target agentic AI system. And this is just a quick overview of the different types of automatic red teaming agents and also frameworks that we have built using the different algorithms I just mentioned for agentic AI. And also recently, together with other collaborators, we have developed this unified platform for agent red teaming called Decoding Trust for Agents platform, which has a large number of simulating environments, allows agents to the target agents to run in the simulating environment, and using this automated red teaming agents that I mentioned to automatically then generate attack candidates and continue to optimize it and so on as well. And with that, I also want to mention our most recent work called Super Red. The goal of Super Red is actually about developing an open ecosystem for this type of automatic red teaming, so that we can bring the community together to build the best automatic red teaming framework and system, so that we can overall together help improve the resilience of agentic AI systems. So the Super Red is designed as an open source framework that you can run, that's modularized, so you can bring in different attack algorithms, you can bring in different evaluation benchmarks, and plug in different types of agents, environments, and so on. So everything's modularized. So, and also with also fine-grained controlled modularized threat model as well. And Super Red allows you to run any attacker against any AI systems with any threat model. And you can find out more information on the Super Red website. And currently, it already comes in with 35 modules to run today. And as the community contributes and plug in new attack algorithms, new evaluation benchmarks, and new environments, this will build the flywheel to have the community together to build this really powerful open ecosystem for automated red teaming. So we welcome everyone to check it out and contribute. And with the system, you also get detailed runtime, for example, observability, transparent insights, and dashboards, and so on. And it's really easy to install, so really encourage the audience to go check it out. So that's on evaluation. Another important part, of course, is on actually building the AI defense itself. And given the complexity of the issue, there's no single silver bullet for building effective defense. Instead, we need to deploy defense in depth, and also deploy and adopt best practice for security, such as least privilege, privilege separation, and safe by design and secure by design, to ensure that we, in the end, hopefully we can actually get properly secure systems. And again, in our overview paper, we actually list out close to 20 different types of defense mechanisms that you can use to build as a layered defense. And also here's one example of our recent work called Progent, which is the first programmable privilege control and guardrail for agents with contextual security, where we allow the guardrail to also automatically generate dynamic security policies to dynamically reduce the agent's privilege to achieve least privilege with the contextual security. So with that, that's the first part, building secure agentic AI to protect the agentic AI systems from malicious attacks. Now let me quickly talk about the second part, which is how we can actually mitigate misuse, and in particular, in the space of cybersecurity. So again, as I mentioned, there's a broad spectrum of different types of AI risks. But for me personally, I do strongly believe that cybersecurity is one of the biggest AI risk domains. And this is also why my group will have been among the earliest to actually working to investigate the impact of frontier AI in the landscape of cybersecurity, and also with our work demonstrating the increased risk in the space. So the key question here is, how will frontier AI change the landscape of cybersecurity, especially given that AI as a dual-use technology can help both the attacker side and defender side? And in order to answer this question, we need to actually do detailed analysis through the complex kill chain for different stages of cyber attacks and also for defenses. And in order to achieve this, my group with our collaborators, we have developed a leading benchmarks that has been used by essentially all frontier AI labs on evaluating frontier AI capabilities in cybersecurity that actually covers across the vulnerability lifecycle, including vulnerability discovery, validation, doing exploit generation, and also patching. And with our work at CyberGym, which is a benchmark containing large-scale, widely distributed open source software, we show that frontier AI capability in cybersecurity is increasing drastically, and also, with recent Cloud Mythos and Project Glasswing, also further demonstrated the capabilities of frontier AI capability in cyber. And also with the recent exploit gym, also showing that the frontier AI now can also automatically generate exploits, and these exploits can even bypass existing standard security mechanisms. And also, as many of you may have heard about the recent incidents from OpenAI Hugging Face, the agent actually, while trying to solve the exploit gym benchmark, it actually broke out of the isolation sandbox from OpenAI's environment, and then actually in the end did very sophisticated attacks to actually in the end was able to break into a Hugging Face infrastructure as well. So all this illustrates that now with the increased frontier AI capabilities, the agents now have really strong capabilities in cyber. The agents, this was not even a misuse. It was not a malicious attacker trying to use agents to compromise another system. The agents actually did this on its own. So first of all, this told us that now with the agent's capabilities, even the evaluation infrastructure itself can now are now becoming part of the attack surface. And also this really is a wake-up call showing the power and the potential risk these agent capability can bring to the world. In order to address all these issues, so first we have launched a Frontier AI Cybersecurity Observatory, bring the community together to do continuous monitoring of the frontier AI capabilities increase in cybersecurity. And also, a bigger question is, what can we do, especially given that AI as a dual-use technology, it can help both attacker side and defender side. And also the challenge here is that coding capabilities and the cyber capabilities are two sides of the same coin. And what's even worse is that we call this the equivalence class problem, is that the same capabilities that can help defenders, essentially in our paper, we show that they can also be used by attackers in the corresponding stage for attacks. And furthermore, there is natural asymmetry between defense and offense. And for example, attackers only need to find one successful vulnerability and exploit and do a successful attack to succeed, where defenders need to defend against all attacks. And also in our paper, we also show a number of other natural asymmetries between attackers and defenders, showing that unfortunately, due to this natural asymmetry, in the near term, AI is going to help attackers more than defenders. So the question is, what can we do to shift AI to help defenders more than attackers? Throughout the history of cyber security community, and also including my own work in the last 2 to 3 decades, we have gone through 3 different paradigms for building defenses. The first one is reactive defense, where defenders develop attack detection and blocking mechanisms, and also other mitigation mechanisms after attacks has happened. Unfortunately, with this defense paradigm, my belief is that, and also our analysis shows that attackers can still benefit more from AI than defenders. And the second paradigm is proactive defense through bug finding, where in this case, the defenders can use AI to try to find bugs in code first and then hope to fix them before attackers. However, in this case, again, attacker also can be at an advantage in the sense that attackers only need to find one successful attack. So we really hope that with AI, it can help us to achieve the third paradigm in a more effective way, which is proactive defense through security by construction. Using this approach, we architect and build provably secure programs and systems in contrast to bug finding and attack defense and reactive attack detection and reactive defense mechanisms. And so through program verification, using formal verification, we hope that we can actually build systems with probably secure guarantees that can completely eliminate entire classes of vulnerabilities and so on. So this ultimately will put defenders in an advantage to attackers. And in fact, we have already entered the era of formally verified systems with many formally verified systems, including microkernels, compilers, and so on. But however, it's been labor-intensive to actually do the proof engineering for the systems, and hence they have not been widely used. And my group has been among the earliest, also with our collaborators, to develop deep learning methods for theorem proving. And I strongly believe that now we are reaching an inflection point. Using frontier AI, we can further enhance formal mathematical reasoning and automate theorem proving. We hope that using this approach, instead of just generating code, we can actually generate provably secure code where we combine the program generation, program synthesis with program verification. And towards this goal, we also have developed the current leading benchmarks for verifiable code generation, including Verna and Vero, which now allows us to evaluate AI capabilities for verifying codes at a large-scale repository level. And we hope that with the community together, we can make rapid progress in this space. And we can now finally use AI to help shift the dynamics, to help AI help defenders more than attackers. So with that, I want to conclude my talk. And I want to just briefly mention that besides this work, we also are developing various work on open ecosystem for agent evaluation, including agents last exam, a benchmark for evaluating agents' capabilities in real-world, economically valuable, long-horizon tasks over 55 different sectors, and also agent beats for building new standards for open, standardized, reproducible agent evaluation. And you can learn more at later today's workshop on future of agent evaluation. With that, thanks everyone.
Can we give another round of applause for Don? That was great. Next up, we're going to have another speaker. We have Oriol Vinyals, VP of Research at Google DeepMind and Gemini Tech Lead. So Oriol, why don't you come on up? Give a round of applause for Oriol.
Hi, everyone. It's great to be back in my alma mater at Berkeley. Today, I know this is about agents, but I've been focused a lot more lately on recursive self-improvement, so I'll try to give you a little bit of my own perspective on it. OK, anyways, so I'll start talking, but the slides hopefully come up. But I think one of the things that at DeepMind we work for a very long time is agents, actually. And it's kind of interesting to see the evolution of what agents have meant to be over the years, especially when you have a company that has been building around reinforcement learning, which defines what an agent is for over a decade now. So my first slide, if it appears, would show the usual traditional reinforcement learning loop, where you have an agent, You have an environment, and there's observations and actions being interchanged. And generally, those are like the agent is powered by a neural net and so on. But then the observations and actions are generally fixed. And the environment at the time, and it makes sense, there's my slides. The environment at the time, we use video games, which hopefully makes a lot of sense today. The arguments we were making at the time, people were like saying, hey, games are not real world. I mean, this is not perhaps going to be as impactful, the technology, as you make us believe. Obviously, hindsight tells us this technology has been and is going to be very impactful. But video games have this very nice property of being sandboxed even more properly than the current sandboxes we have. So we were testing algorithms and idea on the agent capabilities on Go, StarCraft, and all sorts of different games, until, of course, games where we ran out of games, that we had tackled the most complex games and so on. I'll get back to that point a bit later about games. But the pre-LLM era agents, the graph was fairly simple. If you look now at what agents mean, and we've heard so many times in the talks in the morning and now, that I don't want to go too deep into this, but there's a bit of a reshuffle. I think the one that's most profound is that the environment is hard to disentangle from the agent, so I put the environment inside of the agent, right? The environment is like a machine, possibly with access to network, internet, and so on, in which the agent harness that has a large language model as a brain, not that different from that other picture that was at the time powered by a neural network trained specifically for like a game or a domain. But this sort of interaction is so important and so critical that it's very hard to disentangle. And then, unlike before, we have a user that is interacting with this agent, perhaps coding or asking it hard questions that might take a while to run. And the environment in general can be shared with the user. It might be that's my machine. There's also some machines that virtual machines that can spawn on the cloud and so on and so forth. So I'm going to describe a bit what I think, a very practical definition of self-improvement and recursive self-improvement is through this lens. I think it's not that different, actually. That's why I'm bringing it up in the agents section. What SI and RSI are. So self-improvement is kind of a bit of a nuance over what agents are doing for us today. I would say probably the user is not as interactive with the system. I mean, self-improvement means that the system is operating by itself, mostly without much input. So a user might give us a specification, and then this process might run for hours and hours. Or days and days, rather than maybe being more interactive. And then critically, there's a fitness function or whatever the improvement target is or might be. I think in the morning there was a Tetris, right, as the target or the fitness that then the system was trying to optimize. But it's not that different from an agent. It's kind of almost a detail. And then if you go one step further, the recursivity, the simplest way to think about it is like, well, wait a second. The agent harness itself, the code that runs the agent, and even the brains behind the agent actions, the LLM or set of LLMs, now can also be modified, right? So these are trivially can be seen as part of the environment, right? The code that runs your harness, and the model maybe it's an object that you can sort of upload, to your server that's serving tokens and so on. And so the recursive part is just allowing this environment and agent harness to modify itself or the model. And it's useful to distinguish self-improvement in the harness space, right? This is more like the code, how you do like compaction, all sorts of different things that you need to implement for agents. What tools does it have available and so on. And then, of course, also the model weights themselves, right? Which could be rewritten from scratch, could be fine-tuned. And I mean, the action space for the recursivity part is anything that modifies that object, right? So this is fairly simple. I don't think we've seen very impactful actual recursive self-improvement examples yet. Certainly many self-improvement examples. Those are more commonly seen. But of course, this is coming, and it has fairly deep consequences into how we do our own research to develop then the harness and the LLMs, which of course is at the core of what we at many frontier labs are doing. So unpacking a bit, how would you expect this agent with the brain to do recursive self-improvement? It's quite useful to put a bit of my researcher hat. I mean, we all, or maybe not, but many of us have written papers, have thought about ideas to change the field and so on. So the process in which you would expect a fully capable recursive self-improvement system to do is not that different from the process that many of us have been playing as a game for years, to publish papers and trying to get our techniques adopted widely, right? So this can be decomposed in so many different ways, but I think it's useful to think about it in these 4 ways. More detail can be, you can zoom in on one of these and so on. Maybe that's a good point for discussion. But very critically, there's an ideation phase where you take all the previous work, all that you know about the field, and you select which ideas are worth pursuing fundamentally, right? So this is a kind of a very important reasoning step, which makes you go into a next stage of then implementing said idea, right? Like you have to implement it. It might be complex, it might be simple. After which you maybe have an experimentation phase. You run the code, there's bugs, it doesn't work. Maybe you insist, maybe you give up and go back to another idea, and so on and so forth. And last but not least, you evaluate what happened and whether the hypothesis maybe that you form on the ideation phase is verified or not. And then you might obviously traditionally write a paper in a recursive self-improvement system. You might just go back and loop around, right? So what's critical about this, and my observation is currently a lot of effort is done in the middle 2 boxes. Implementation, I mean, we know how powerful coding agents are these days. So I think there's certainly a lot of progress and enthusiasm behind implementation and experimentation as well, like running, compiling, debugging. Also, I think we've seen, perhaps because it's the most interactive with the user, so more similar to self-improvement rather than recursive self-improvement, we've seen a lot of progress there as well. But the other 2, not so much. So I'm going to zoom in a little bit onto kind of some maybe thought-provoking thoughts on what might happen and what needs to happen for us to really achieve this loop meaningfully with full automation. So evaluation is always a very important topic. I find as a community, evaluation and data have never been perhaps highlighted as much as they should have. Even different papers that propose a new data set might have been regarded as an application and not worthy of publication in one of the bigger conferences, certainly years ago. So I want to insist on evaluation because it's so critical. So how do we measure progress in a more like scientific way as we are developing better models and better harnesses, right? The first way is kind of the obvious way. We take some capabilities we believe are important in this and some benchmarks. So SwiBench Pro, MLE Bench, perhaps Perplexity on held out data in pre-training is commonly what most people are optimizing for these days. And then you just hill climb, right? You just say, look, we're going to get better at all these, and hopefully by doing these, recursive self-improvement might emerge. And certainly there are pros for this approach. I mean, this is exactly how we've been training LLMs for a few years now. Evaluation is reasonably cheap. We know how to do it. It's well-defined. But I mean, the cons, I would say the one that is the worst is that it's very indirect measurement of actually a system that might truly develop recursive self-improvement. And of course, there's all sorts of issues with overfitting, cheating, and also the current evals, at least that we have, are focusing, as I said, mostly on those 2 middle boxes, implementation and experimentation. Now, a much better way would be to evaluate literally for what we care to improve the capability of, which is, in this case, recursive self-improvement. There are some benchmarks that are appearing, because, of course, this is gaining traction in the field. Post-train bench is one example, but Don was telling me about another one. So we're going to see this popping over the next few weeks and months for sure. And, of course, the advantage is that we measure what we care for, right? So we are improving the self-improvement capability. If we set the evaluation in a way that is like, hey, the inner loop itself is like, hey, evaluate some other metric, go for a few tries and see how much improvement you get, right? That's your evaluation. It's a bit meta, but it's more powerful. Of course, there's a few cons. This is expensive, right? Now to evaluate, you literally need to run an agent for a while to improve some set metric. And then the inner loop still will be, I guess, improving Tetris or something that is not perhaps the actual metric that in production we'll care to evaluate, which would be, hey, I want to automate my whole frontier lab, create the best model in the world, right? And I mean, these evaluations might be a bit out of distribution as they stand today. And then perhaps a modification of this, very relevant for what's been the discussion of the day, and certainly what I expect to increasingly happen in the field, is to tweak the previous one by also not only evaluating for, hey, how much can I better play Tetris over 3 hours of compute that I give this agent, but also how do I achieve that improvement, right? I don't want to see cheating. I want to see creativity. I want to see certain aspects of intelligence and evaluate them with some powerful reward models that are a bit more fuzzily evaluated, but still very important capabilities that we expect this model to exhibit. So an example, just to give it a concrete and maybe to use ideation as, I think, a fairly underexplored area in general in LLM training. So, well, how do we evaluate ideas, right? Well, there's many aspects. If you are a reviewer in a conference, right, you're looking for research taste, novelty, efficiency, elegancy. Is this going to stand the test of time, this kind of technique, and so on and so forth, right? So you can imagine trying to evaluate the behavior of an agent doing recursive self-improvement on that ideation stage based on a few of these that we can write rules and try to automate a little bit. But it's very hard at the moment. These are very understudied. So I think this is going to take us some time to figure out, to advance these capabilities and the reasoning, the automatic reasoning that might be required for us to be able to optimize with reinforcement learning on top of this system. And I would argue, even as humans, are not that good. I mean, we have very expensive systems, conferences, review processes, and so on. And transformers actually took many years to become mainstream. Distillation, which is getting more famous now, was actually rejected from the conference we submitted at. And it took many years and some sort of random process for it to reemerge as, hey, this might be actually useful. And I mean, all of you probably have your own sour, rejected paper story of a great idea that in hindsight you should have been accepted by this automated and expensive process that we set up. So automating this truly in an agentic way might take some effort, but it's worth pursuing to achieve RSI. Of course, we've seen, and I bring back the games here, this is not a surprise that our agents are sort of doing things a little bit differently than what we expect. So we had very famous games that are exploited in some different ways. The other video doesn't work, but it's also quite funny. So this is many years that we've seen this coming. And then to wrap up, right, we need to, obviously, it's an incredible time to be alive, right? It's definitely clear that RSI will increase perhaps 10x or more the speed of progress of certain engineering and science tasks for sure. But be mindful of how we set the goals, misalignment, resource reallocation, how the labs are run might change. So we need to be quite careful about how to take different steps in this. And as I was arguing, it might not come as fast as we thought it would, because first, evaluation is very hard, and ideation is also very hard. So these are two important components. Also, some processes might be just limited by physical constraints. I mean, the chips cannot go faster than what they're designed to be. Of course, also like speed of light and so on, right? To transmit data around like the chip and so on has also certain limitations. And then last but not least, performance that we had obtained as humans might be close to an asymptote. So by adding recursive self-improvement, we might anyways not see a drastic improvement, right? So how good is AlphaGo with respect to the perfect Go game? Unclear. Or another example is sometimes it's kind of annoying how well these models write, and you have to make it look a little bit worse. So they got too good at writing, for example, right? So there's some of these domains certainly where better doesn't mean better necessarily. And with these thought-provoking thoughts, hopefully we can have a good panel later, but looking forward to the rest of the session. Thank you very much. Thanks.
All right, thank you, Oriol. So next up, we're going to have a talk from Wojciech Zaremba, who is a co-founder of OpenAI, and he recently has started working as the head of AI resilience at the OpenAI Foundation. So everyone, give it up for Wojciech.
Okay. Wonderful. Thank you, guys, for having me here. Okay, slides. So, as it was mentioned, I'm part of OpenAI Foundation. This is like an interesting entity. OpenAI went through restructure a number of months ago, and now there is a non-profit that owns around 1/4 of OpenAI equity. So that's like a massive amount of resources. And one of the divisions of OpenAI Foundation is AI resilience. I'm going to explain today what AI resilience is. And it's similar to AI safety, and yet it's different. So today I will explain what AI resilience is. And I found it to be the most useful to explain it through analogy to fire resilience. And then we'll go into what does it mean for AI playing out well. So the way how the presentation will go will be at first describing similarities between fire and AI. And obviously, fire is very different than AI in many, many ways. So these are by no means perfect. So both fire and AI are general purpose technologies. It means that they have really broad applicability. In case of fire, it is used to heat food, provide warmth to people, smelter metal. It's part of engines. It's pretty much fundamental to our civilization. Something similar is happening with AI. AI is now part of the knowledge and wisdom development, part of the scientific process. And also, if you take seriously where robotics is going, it will be just the fundamental part of the economic engine of the future. So both AI and fire are general purpose technologies. Okay, that's one similarity. Another similarity is both technologies come with risks. So in case of fire, there's like a number of major fires in the past. London was burned 4 times, Boston, Chicago, 80% of London was consumed during the large fires. Now, today, we pretty well understand the risks coming from fire. That's less true about AI. When you ask people about the risks of AI, it's kind of like a people point in different directions. There are like many things pointed out. It's just enough to open newspaper and hear what people are scared about. And I would say these risks are highly uncertain. It actually might turn out that some of these risks will end up being a vaporware, and some of them will turn out to be 10x more than what people expected, and some of the risks might not even be at the least. Okay? So fire and AI, they come with risks. Okay? Here is like an interesting twist in the story. So it turns out that in case of fire, the way how people try to provide the safety for fire was through restriction. So curfew comes from French, and it means extinguish fire. In the medieval time, it was common that if you had fire going on at your home during the night, police would come and knock at your door and ask it to extinguish fire. So obviously that had that's like a decrease of capabilities of the fire. And it also turned out that at least in this particular case, actually, it didn't work out well. The Great Fire of London happened despite of curfews. So the method of restricting fire didn't actually work out for this particular technology. Now, in case of AI restrictions, this is like a more complicated. There are some restrictions that actually seem to be working pretty well. An example would be most of the platforms, they follow non-consensual intimate images restriction. They don't allow for this. Now, some people advocated for open source restrictions, and these are not really implemented. So I would say that in case of AI, the restrictions didn't work out well. So now you might ask, what did it take for Fire to become safe? And it turns out that there wasn't silver bullet. It's not that there is a single solution to make Fire safe, and it ends up being multi-layered ecosystem approach. So you have these systems for early detection of a fire. There are also people who are trained toward dealing with fire brigades. They have special vehicles. There are fire trucks. They have specially designed hoses. Now, there is also it turns out that the cities, they have a supply of water spread throughout the city with fire hydrants at the sufficient pressure and the quantity necessary in order to extinguish fire. There are also materials which are specially designed. So there's like we switch from wood to metal and concrete. There are also inspections, insurance, and also, let's say, designated areas for exit, and so on and so forth. So once we implemented this, actually, now fire is not something that we are particularly worried about. So we are in the place that none of us is worried about this particular risk, because we are able to really fully harness the benefits. So you might ask, actually, did it even work? And the claim is it actually worked remarkably well. So these days we have cities which are order of magnitude denser than the medieval cities. We have many more sources of fire. So there's like, let's say, electricity, gas industry, and even data centers these days. And fire is not something that people are worried about. So now you might ask, OK, what would it be analogous for the AI itself? And I find that people in AI space, they try to think about a silver bullet, that there would be one solution in order for AI to play out well. And I actually think that that's an incorrect way of thinking about it. I also think that it's not just enough to make individual models aligned, though that's like a part of the solution. There needs to be a number of solutions in the ecosystem. So what I mean by that, let me give you some examples. In case of the models become, for instance, quite capable when it comes to biological domain, and many people foresee the risks coming from models making it easy to manufacture pandemics. Now, if we think that that's the risk, then dealing with these risks requires, and if we also assume that there will be diffusion of advanced open source models, then it might not be sufficient to guardrail these capabilities within the frontier labs. That's like one of the things that should be done, but that won't be enough. We might need to harden the environment itself. So for instance, in that space, people are thinking about ideas like sanitizing air, because if air is sanitized, then actually pathogens wouldn't be able to spread. Maybe in case of cybersecurity, we need to get to the point that the software is formally verified. That would prevent it from being hacked by superintelligence. Maybe in case of safety accidents, we need the public database, similar to how it's happening in case of aviation, that the incidents are being publicly reported, and the ones who reported gained by reporting safe harbor, and so on and so forth. So now, creation of these might, some of them could be achieved through creation of the companies working on these efforts. Some of them might be achieved through the creation of the nonprofits. But like fundamentally, we are in the place that it would be important for a number of capable people, for people who are like a reality warping, for people, CEO-like figures, to ask themselves what needs to be built in the world for the AI to play out well, and then to go after building the new institutions and organizations. And in case of OpenAI Foundation, we have tons of resources to support endeavors like that. And whether or not AI resilience will succeed depends on people in this room. Thank you guys very much.
All right, thank you, Wojciech. Very fascinating. Next up, we have Jerry Torek, who is going to speak with us. He is a former VP of AI research at OpenAI, and now is the CEO and co-founder of Core Automation, one of the most interesting new AI labs startups. So give it up for Jerry.
Thank you very much for inviting me. Very happy to be here. Long horizon agents are clearly one of the frontiers of AI research right now. If I look at my Codex session, my median usage is around 10 minutes. If I look at the mean, it's around 20. Why is it not more? Why agents are not working for me for a longer time? I think it's a very worthwhile question to be asking today for AI researchers. But to start with, let's start with the obvious, which is we already live in the era of agents. Agents are here, but we are very early in this era. In my mind, O3 was the first really agentic model, and that model was really released in April last year. So we are just barely more than a year in the era of agents. That means the models are very early. They have improved vastly since O3, but at the same time, there's much more improvements to be had. The products are improving, the adoption is coming. A lot of things are still not figured out. And we live in those beautiful times and that beautiful opportunity to figure those things out for the future decades of agent proliferation. Even thinking about the definition, what makes agent an agent? I think agent is a very fuzzy term that is hard to fully define what it is. For me, like I put some pieces that I think make an agent, which is agents use tools, because agents should be able to act on my behalf. Agents are most likely async. I tell agents something to do, and it goes on and does its work. Agents are usually goal-oriented, which you specify something high level, what you want the agent to do, and the agent fills in the blanks. And agents are working usually over long horizons of time. You don't do back and forth every 5 minutes. You let agent do its work for extended periods of time. And whenever we extend the length of the time that the agents are working, there is this pretty obvious observation that with every step, the neural networks that we train are probabilistic. They make failures. So with every step, there is an exponentially growing through the length of your trajectory chance that something goes wrong. And that was a very big reason why we couldn't have agents for many years until very recently, because the neural networks were getting off the rails. And this is pretty like classical assumption from the reinforcement learning literature. And why do we need actually reinforcement learning? And the moment happened when me and my team were able to scale reinforcement learning to larger and larger amounts of compute, where we finally found a recipe that allowed us to train models to recover from their own mistakes, train on their own trajectories, and that suddenly started making the models be able to succeed in harder and harder tasks. And what did we see? The first thing is obvious, like the more compute you spend, like you could see proportionally on a logarithmic plot the capabilities of the models improving, but we have also seen the other thing, which is one of the most important shifts in machine learning of the recent years, which is the more the model thinks, the more tokens it spends on a task, its performance improves. So not only the models trained with reinforcement learning were not falling on the trap of exponentially increasing the chance of failure on a trajectory, they were able to recover from that, but they were able to even keep productively thinking for longer and longer. So essentially, the longer your trajectory, the better the results you are getting. We entered the test time compute era and token maxing. So Then we have this now. This is a plot a lot of people thinking about agents are very familiar. It's a plot for how long agents can work from us. And since we started scaling reinforcement learning, it reaches new and new heights with the latest readouts of around 12 hours, 16 hours for some of the best frontier models of the day today. So the question is, maybe this is it. Maybe we have reinforcement learning, it works, we can throw a lot of money at it, and maybe we just keep scaling and we'll have agents working for whatever amount of time we would like. Is that the case? Is that the solution? Unfortunately, there are problems. There are challenges. I don't think we are done yet. The first problem, which is that the economics is here kind of unfavorable in many ways. To sample a trajectory of length n, generally your cost is proportional to the length of trajectory. If a quadratic attention is even slightly bigger, but let's think for a second linearly that the cost of each token is fixed. So to sample a trajectory of n tokens is proportional to the length of it. But also how our today's reinforcement learning algorithms work, they assign single reward for that trajectory, which is there aren't really any in modern RL credit assignment methods to assign that reward to any specific tokens, which means you get one reward to the trajectory of n tokens, which the information per token you are getting is roughly 1 divided by n. And the cost of that trajectory is also n, which means that your learning signal decays quadratically in the length of your trajectory on the horizon you are doing. Which is if it would be linear, it would be like pretty okay to keep throwing more money, and we know if we want to train agents to work twice as hard for twice longer time, we need to spend twice more money. That's a pretty reasonable thing, but if it's quadratic, it is becoming pretty brutal. The big labs today are very good at spending a lot of money training models, but the quadratic cost makes the scaling of that considerably harder than it would seem at first sight. The second bit, which is even harder, is latency, because as much as there's more and more investment coming to the AI world nowadays, no one has time. There isn't that much time. And the latency problem comes from the following. Imagine you have to sample a 12-hour trajectory of an agent. It takes 12 hours to sample it. And then you take a gradient step to update your model to reinforce the successful trajectories. And then you have updated weights, and then you sample another 12-hour trajectory. You are able to do full 2 gradient steps in a day of your reinforcement learning agent. That means roughly 14 gradient steps a week. That means like 60 gradient steps a month. It is not a very fast training method, and no one has time in today's world. So training for very long trajectories and for long horizon thinking is meaningfully very, very hard, harder than many realize. And all of the progress in the field, and the reason we have even any agents that can think for a long time, is usually we put some kind of harness on top of it, because the agents are very good at doing short horizon things, short horizon tasks. And the truth is, a lot of long horizon work can be glued very successfully together from doing smaller and smaller things. And we have these things called /goal in Codex and Cloud Code, which is very powerful. We just create a fixed goal for a model. It runs for however long it can, then it revisits itself, and it continues to do that. We have plan mode. We have many ways. We have sub-agents. There are various ways that are not native to the model. They are not back-propagated through. They are not trained, but to utilize the model's ability to work on shorter-term goals and structure from them being able to spend more and more. They are very successful, but the history of machine learning has always been that whatever we can backpropagate through wins with things that we cannot. Everyone's probably pretty familiar with auto-research and what auto-research means. And the story of almost every auto-research rollout is you get a lot of progress pretty early, but if you go further and further along, it kind of stalls, it kind of stops. I haven't seen yet today, with today's models, any particularly successful auto-research rollout. I think research is one of those tasks that is inherently hard, serial, and long horizon. And today's models, it's not very easy to glue it from a small horizon thinking to think about larger scale research projects, and auto research is one of the places where we can definitely see it. So a lot of the questions like I am asking myself is, how did humans master pursuing long horizon goals? Very famously, Andrew Wiles spent 7 years working on a single goal of proving Fermat's last theorem. He was successful. It was a seven-year project. How do we train our models to do seven-year projects? And thinking about humans even more, like I've asked ChatGPT, at which moment did humans start developing long-term planning? And what ChatGPT has told me, that we have until today roughly 10,000 generations of humans since the moment we were able to start doing any significant long-term planning. Since that time, there was roughly 120 billion people. So maybe this is it. Maybe we need 10,000 gradient steps and 120 trajectories to sample, and maybe that is what allows us to optimize for long-term, long horizon planning as well as humans do. Also, gradient descent is more sample efficient than evolution, so maybe we have even more, and that's something for us to think about and revisit. The value functions as a research direction is one thing that definitely can help. It's if we got good value functions for AI research, it will be extremely helpful. I think the research on value function has been, like, at some moment we basically threw out value functions when doing reinforcement learning on large language models, and everyone has seen that it works as well. Value functions are very, very hard problem. I have some amount of skepticism in how much progress we can do on really good value functions. Very often finding good value function is much harder than solving the problem we are trying to solve. But if someone figures out value functions, we're good. We can solve as long horizon problems as we would like. Maybe continual learning is the answer. Continual learning tries to solve this problem from the other side. We try to update the model for the loop. If we have long horizon 7-year loop, let's prove this theorem, and we repeat the same thing every day, but we don't repeat it with the same model, because the model updates on the new data. Every day the model learns something, the model improves, and the model gets better. I think continual learning would be able to get us through that very, very well. The question is how. And this is an unsolved problem. This is a problem that is worth solving. And if someone is looking for what do we want to work on right now, right here in this age of machine learning, I think long horizon agents is absolutely one of the valid choices. When we get that technology, we will be able to put agent towards working on hard research problems. We'll be able to have them to run companies. This is a very long horizon task that is very, very economically valuable. And if I want to delegate to an agent, I don't want to be telling it what to do every 30 minutes. I want to be able to act on my behalf for a long periods of time. And I think this is extremely valuable. So the research is not done. There's much work to do. And the objective is agents that can keep going for us and keep getting better over time. Thank you very much.
All right, thank you, Jerry. Very fascinating talk. Next up, we're going to have Dan Roth give a talk. He's the chief AI scientist at Oracle and also a professor at UPenn. He's been a professor for more than 20 years. And at Oracle, he has a bit of a view into everything going on in the AI race. So please welcome Dan.
Okay. Hi, everyone. Really excited to be here. So I'm going to change gear a little bit and talk about data, how we use data, how we access data. And you'll see in a minute why I call this AI for data and data for AI. But mostly, I'm really excited about the promise that Gen AI has for data. So really, we are going to move from the messy world of using a lot of types of data, different representation, different types, where people need to learn the domain, need to learn how data is represented, need to transform data from one format to another, and need to understand how to fuse diverse data to a much cleaner way, where we'll be able to actually work with data in a conceptual level, our own terms, our own metrics. And what adds to this excitement is the fact that really a large amount of data that exists in the world is going to remain outside a language model. So you know, language models have swallowed a lot of the data, and you know, this is why we have powerful agents today. But there's really no more general purpose data. A lot of the general purpose data has been swallowed, as I said, by model provider already, but there is a lot of data out there, data that belongs to corporations, data that belongs to financial institutions, government agencies, people, and medical centers, and this data will stay outside the models. And it's going to be dynamic. So the question is, how do we deal with this external data? And I think that one of the key use cases of Gen AI is going to be that of orchestrating and supporting access and use of external data. And this is true for human consumption, but it's as important when we think about agents using data. Think about your coding agents. In order to develop coding agents, these coding agents need to access a lot of data, from design documents to tickets, maybe to correspondence about what happened in previous generation of the software. They need to access heterogeneous knowledge sources and do something with this. And this is difficult. So reliably supporting decisions that depend on retrieving and using data is extremely difficult, more difficult than we kind of think. And it's difficult for multiple reasons. It's difficult because of information retrieval. Hopefully, this will move at some point. There is a myth that information retrieval works, but you know, try to search your email and tell me whether it does work. Understanding information needs, understanding the stored data, using data, all these are extremely challenging in today's world. And it makes all this business of knowledge access and use very difficult. So in most cases, we are thinking about AI for data, sort of how to use data or how AI can help us to use data for our own human consumption. Ask what AI can do for you. But really, we care about data for AI, because in order for us to develop agents, agents need to access data, to access a lot of different kinds of data. So this relationship between AI and enterprise data is really not one-dimensional. While AI unlocks value from the data you already have, the quality, the structure, the governance of your data really determines what the agents, what AI can actually do. So understanding both sides of these equations are really important, and really the difference between AI that works and AI that may not work. So really the data layer underneath agents is crucially important and very difficult to build. So, so think about agentic capabilities and what kind of data we need in order to develop them. Think about, you know, the 17 different types of documentation that exist. And think also about just trajectory data, operation data, tool use traces, and all this data that your agents need in order to be able to actually do what you want them to do. So why is it so hard? There are many reasons for this is hard. There are some core difficulties, you know, retrieval. Really, information retrieval isn't working unless the way you present the information need is lexically close enough to the way the documents that you care about are represented, which typically doesn't happen. So this actually necessitates developing a semantic data layer across heterogeneous knowledge sources. So first of all, you will bring the representation of the data closer to the way information needs are expressed, but also so that you will not care about where is the data coming from, which data source it's coming from. We need to deal with structure. So people think about NL to SQL or NL to other formal representation, and this transformation is very difficult, partly because it depends also on retrieval. If we want agents to use the data, again, we need information, them to access multiple knowledge sources, and we need expertise for each one of these knowledge sources. We have rich documents today. More and more rich documents are being stored, from papers to figures, to video, to images, and the information inside this rich data is actually not exposed to your retrieval. unless you do something to expose this information, and then maybe some pre-processing, maybe some stuff that your agents may or may not do. As I'll show in a couple of examples later on, planning how to access data, in what order to access it, how to filter one source by another is a very challenging problem, and not to mention conflicting information. Think about your file system or your email, how much conflicting data is there, and we want our agents that access data to actually do something well with this. And of course, there are reasoning challenges. Reasoning, in many cases, is beyond the capabilities of general purpose models. And under all these kind of core difficulties, there's issues that have to do with governance, policy enforcement, reliability, consistency, auditability, that if you want to use large-scale data in the context of a corporation, medical center, and so on, you really have to deal with. And optimization, so in the first generation, we don't care so much about cost, but we do care about cost. And how to think about when do I process data offline, when do I process it at runtime, how do I cache computation, how do I use query logs and history, all these are really difficult problems. So we actually are trying to work on all these aspects of the data, and I'm going to try to give you one slice of this, an important one, but not the only one, from the perspective of NL to SQL. And I'm going to give a shameless plug to some results that some of our teams at Oracle have done in participating in competitions like Spider 2 and Archer, and doing really well, kind of leading on top of the leaderboards in this. But beyond the shameless plug, I want to actually point out the absolute results. So you can look at Archer, where the results is actually 55%, or Spider 2, where the results is just low 70s, which means that we are really far from being able to address these issues of accessing data and using data properly. And I'm going to illustrate this with the following example that hopefully you'll find interesting. So I'm very interested in tennis, and I follow tennis closely. So I'm using tennis as an example for a lot of the things to kind of show capabilities. So here is a question that I asked just a few weeks ago. I presented to a top model. Give me a list of the European male tennis players sorted by their tennis income, only tennis income. So if you think about it, it's a very complex question because the model needs to know who are the players, which country they're coming from, is it in Europe or not, then go to tournaments they play in 2025, how much money they made in each one. But and the model actually gives me the way it thinks, which sources it goes to, which tables it goes to, which pieces of text it goes to, and at the end it gives me a nice table. Now, first of all, before I analyze the table, think about how cool it is. This is really the promise. I just express my information need in natural language, and the model devised it. He gave a plan, accessed many information sources, structured, unstructured, web, used its parametric knowledge to know where the countries are, and so on, reconciled conflicting information because there's a lot of conflicting information out there, aggregated it, and summarized it into a table. Beautiful. Now let's look at the details. Look at these two entries that I point to in the arrows, and you see that they're not sorted correctly. This was the most surprising mistake to me because the model should have called the tool to do sorting properly. Never mind. But even more interesting is someone is missing. I'm sure some of you will be able to tell me who's missing from this list. Alcaraz is missing. So the model forgot Carlos Alcaraz. Not nice. And you can also look at these two players that I point to, and you'll see that their income is identical to the dollar. So they made millions of dollars, and the income is identical to the dollar. Cannot happen. Clearly a mistake. So what's happening here? So really, it's a very difficult task. The model needs to optimize access across knowledge sources. Now, it can go about it through a list of players, generate a list of players, and then figure out whether they are in a European country, which tournaments they play with, how much money they made in each tournament. Or it can go to the list of tournaments, and then look at each tournament, who played there, how much money they make, and so on. Now, there's a lot less tournaments than players, so maybe this should be the right way. But on the other hand, tournaments and data are more noisy. So it really, doing this right really depends on understanding the data and the domain, which is very difficult. In tennis, it's possible. In most cases, it's just impossible. So while agents are doing this faster than we can, they're prone to errors and high cost. And most importantly, if you think about it, and I did remind the model that he forgot Carlos Alcaraz, and he added Carlos Alcaraz, but if you look at it carefully, you'll see that a few other things changed. For example, Andrei Rublev, number 7, completely disappeared from the new list. The money changed a little bit, so someone, Zverev, that made over 6 million before, now is making less than 6 million. So it's not consistent. But really the important thing that I want to point out here is this is tennis. Really, who cares? And I also know the results, so I know how to kind of look at it and decide whether it's correct or not. But if this was the same question that you ask about your financial analysis of your company or any other sensitive information, the notion of visibility of failure is really important. We should be able to address this issue because without it, we cannot use these kind of systems reliably and consistently. So I want to stop here, basically remind you that real-world data is multimodal, temporal, multilingual, heterogeneous, and we really have to do a lot of work in order to unlock this information. And understanding both sides of the equations, AI for human consumptions over data, and data for agent consumption, or using data for agent consumption, is really the difference between AI that works and AI that disappoints. Thank you.
Okay, thank you, Dan. Next up, for our last talk before the panel, we have Weiju Chen, who is a technical fellow and corporate vice president of Microsoft AI. He co-leads foundation model development, including their coding and agentic models, and he was the last author of LoRA, the industry standard technique for efficient LLM customization. So, Weiju, everyone welcome.
Thank you.
Thanks.
Yeah, good afternoon, everyone. It's good to be back here. So I think today I'm going to talk about two very simple things. One is what drives the continuous model improvement. And the second one is what's the next for the continuous model improvement. So the first one for the continuous model improvement, I think everybody think about, okay, is the compute, definitely. Compute is the first very scaling engines. Without a compute, we cannot do anything. So basically, I think you can think about a lot of this kind of improvement basically was driven by the compute. There's more compute there, and so the model will become better automatically if you train it longer. So on the other hand, actually, you also, this kind of the more compute, you also unblock a lot of this kind of experiment. And a lot of innovation basically is also from the experiment and also this kind of fast iterations. So from the compute, definitely for today, there's 3 dimensions for the compute today. The first one is the pre-training. Pre-training, when you have the large model, when you have this kind of more data, and for today, it's also more exploration. This exploration came from the model, or it came from the human. When you explore more, definitely, you are going to make the model better. I think that is basically a lot of people call it as the pre-training scaling law. The second one is the post-training. So for the post-training wise, so definitely, I think for post-training today, a lot of simple problems are already solved. So the computer is more focused on how can we solve the harder problem, or how can we solve the longer problem, long horizon, and also how can we solve this kind of the multiple agent problem in the training. It's not just in the inference. So basically, we can also call this as a post-training scaling law. So the last one definitely is the test time compute is for the product serving. So basically, it's about how can you make this kind of the COT, this kind of the family of model interact together. The other one, definitely, is the data. So we always say data is the king, everything else is the queen. And also, data is the oxygen. So basically, data, you can think about data is a second engine to make everything happen. But basically, there are 2 kinds of the effort in the data. One is the pre-training. Pre-training, so if you go to see, most of the pre-training making progress is also because of the data. Every time, when you're able to clean the data much better, when you're able to refresh the data, because the web data is also becoming better and better every day. And also more and more coverage. this kind of synthetic data is not just about the quality. The most important is the coverage. It's able to create a lot of complementary data than before. So this basically is also trying to make this data much better for the model building. So synthetic data, I will talk a little bit, and actually I think is the most important thing in the future, one of the most important things. The second one is the human data, probably. All the data we create every day will be the seed for the synthetic data. That means synthetic data will be the mainstream in the future, and all the data we have. Actually, it's just to how can we produce a better synthetic data. The other thing about this kind of the power training basically is about this kind of the RL environment. How can you make the RL environment to run as the same as the user used that during the training? So RL environment will basically make the model to be more useful for the product scenarios. And because RL needs this kind of the try and error, so definitely you need to make this very similar thing in the inference, get into a training. So basically the model is able to learn. So this is also very similar as about how can you build a simulation in the training. So you are able to generate unlimited data. So basically that is the key for this kind of the RL environment. The third one we talk about is the model architecture. This is very complicated. There's so many papers about the model architecture, and there's so many details there. But I think I want to summarize basically is about there are 3 dimensions, all this kind of thing trying to optimize. First one is definitely you want to build a much higher quality model. Second one is the lower inference cost. So a lot of people just ignore the second one. And the last one is definitely for today is how can you support much longer context, make it more efficient. So the goal is also pretty simple. How can you make it better and cheaper? So, and based on this kind of, I will try to believe actually for data is more important than the model quality. Model architecture actually will pay more attention to the inference cost and inference efficiency. How can the model be more popular? Finally, it's going to be decided by how fast you're able to run and how cheap you're able to run. I think that's more important. So we need to define the inference at the beginning. The other one basically is based on the GPU advancement. We need to put more compute instead of more I/O to less I/O but more compute. That's also important. The next one I want to quickly talk about actually is about a lot of people are talking about is the distillation. And distillation basically we think about for the machine learning, a lot of things actually is just about distillation. It's just about you are just distill from human or you distill from model. When you distill from human, for example, when you learn from all this kind of the existing data in the web, you distill from human. When you learn from this kind of the product telemetric data, you also distill from the human, this interaction. You are also basically, when you ask a human to label data for us, actually you also distill their knowledge. So distillation actually is a very popular thing. So we distill from a model, definitely, I think this is very, it's very popular as well. And so, basically I was thinking about distillation, basically, you can think about in the industry is much more efficient than this kind of the RL training. Is also, we don't need to build anything from scratch. So basically, I believe the next better model basically was built from the existing model instead of trying to build anything from scratch. The next one is distillation is also a very general pattern. For example, you're able to build multiple teachers because it's easier for the RL to learn from one single specific teacher, and it's also able to run in parallel for this and distill into a single model. On the other hand, I want to say distillation have a lot of this kind of the research, have a lot of new problems coming. It's not just about a simple problem. It's a very important problem and for example, there are so many different kinds of distillation, just like you're able to distill from strong model to another strong model, or you're able to distill from strong model to weak model. And basically, you're also able to distill from the weak model to the stronger model. It's also possible. There's also a lot of research we need to deal with every day. For example, just like a more powerful teacher model, a more powerful model doesn't mean it's better teachers. That's very similar as humans. And also some weak model, sometimes it also can be a very good teacher model. So everything is possible for the distillation. The next one we want to talk about is RL, definitely. What RL works pretty well today is about it's very efficient. It's very effective, not efficient. It's very effective to solve the problem, no matter it's a verified problem or non-verified problem. It's also very good for us to solve the product behavior. If there's something wrong, we just define a grader. We just put some data, and then actually it's much more efficient than other approach. And it's also very good to work directly to the real environment. But there's also a lot of things actually I believe RL distillation and the synthetic data maybe is good enough for us to get to the self-improvement. So, but I think there's also a lot of challenges for the RL as well, just like it's very slow. And I think a lot of breakthrough need to happen to make it much faster. And it's also, the update is also very incremental. When you run the RL chain, you will see the update is very incremental. Just like maybe sometimes the LoRa update is already good enough. So, and on the other hand, actually, is the data. So what drives the RL is the data. Synthetic data definitely will be more important for the RL chaining. And I also believe maybe 99.9% of the data actually are coming from synthetic data in the next step. So I think we already talked a lot about the harness for today, so I will be quick. So, and one thing I want to say is about we should try to optimize the entire system. And harness is a very big part in the system instead of trying to optimize the model. So because there's a lot of builder here, I want to say, so before you think about to optimize the model, try to optimize everything around the model, not the model itself. So before you try to optimize the model. And the other thing is about, I want to say, the harness you built today, a lot of things will be observed into the model at some point. The harness will become simpler and simpler. And we need to define, but definitely at the same time, we are also define more and more complicated scenario and build more and more complicated harness. Model is going to eat a lot of things. There's nothing we're able to change. So for the last one, I want to mention actually is very important for us is we just not care about the benchmarking. We also care about the production, this kind of the usabilities. And usability actually, this kind of the interaction data actually is very good for us to build a better model. It's not just about this kind of the benchmarking. So, and by default, actually, I think the continuous model improvement really require a continuous deployment at scale. A lot of people are going to use your model, and actually you're able to understand what is going wrong, and based on these interactions data, and also able to see what other model do for this scenario, and get the insight and trying to learn from there. And this is my last slide, and it's about a feedback for the next round. I think first one is the scaling is keep working, and we also don't know what's the ceiling. And the other one, definitely, the model is already able to optimize the harness. It's also able to optimize and change another model. I think that's also going to happen because model is better than human for this. And the other one, definitely, we want to optimize the whole system. And the synthetic data will become the mainstream, especially for the next model training. And the last one is also very important. Human is still involvement is still very essential. We still need human to guide the model, how to do the model. Especially for the last one, how to make sure this self-improvement align with the human's value instead of doing something the model want to do. Thank you.
All right. Well, that was a fascinating number of speeches, and now we're actually going to have a panel with all of these people. So if everyone could welcome out all of our speakers. We're going to have about a 20-minute discussion here. All right. Well, so we're very lucky to have this group here. A lot of the people here are responsible for the way AI looks today in the real world. And everyone here is also working on how it should look in the next couple years. So I think this is a wonderful opportunity to have this discussion. We're not going to shy away from the hard questions. So I guess the first one is, maybe just to start high level, like, do we have the right architecture to get to this next level of AI? Do we have, are transformers the right thing to get to RSI, continuous learning? I think I want to start with Jerry on this one. Let's start here.
Okay, it's a spicy one, but I feel like I'm being asked a lot about it. And my theory of AI research is that you always should try to think, what is the bottleneck of the day? What is the thing, why are today's models not 10 times better than they are right now? And while doing what we've been doing and keeping investing in transformers, building new environments, scaling up training, gives us gains. Those gains are predictable. We already know how to do it. I think architecture is the biggest thing that can give us gains beyond those things that we already know how to do. I genuinely believe, and record this, remember that the next 2 years will be the time of architecture, where the biggest gains and the biggest progress in the deep learning will come from like trying to step away from the transformers. We have been the discovery of transformer has been an inflection point for AI research. Like scaling transformers and doing pre-training has been another moment where the age of scaling has started. But transformer has carried us very far, and I think it is kind of like a little bit like holding us back right now, where I believe for the same cost you probably can train much better agent with a different architecture. We just don't know that architecture yet, and it's a time to find it. That's what I think.
Oriel, you guys are working a lot on, as you just said, RSI. Do you think transformers are the right thing to get us there?
Well, first of all, I guess transformers have transformed over the years. So, like, if you look at the actual model today, it resembles, but it's not the same. So every iteration of a new model we see outside, especially the ones you can also see in the open source, I mean, there's a lot of tweaks in the architecture already happening. So definitely there's a hill climbing, perhaps to Jerry's point, is a bit of a local optimum around the transformer, but that's very important. I'm not sure I would believe that I mean, is there a better transformer-like thing that is much more efficient? Possibly. I feel like when I think of architecture, I think holistically, not just the brains, but also the whole agent that you build around it. That architecture, I feel, has a lot of more low-hanging fruits to optimize, like its memory system, how it compresses context, and so on. So I would probably bet on disruption there first, although I'll be rooting for, obviously, better architectures that I'm sure they'll publish in NeurIPS 2027 or so.
No comment there, I guess. Don, I'm curious for your thoughts on this.
Oh, yes, this is a very good question. I was talking to Jerry earlier. The question is, which way will go faster? Yes, I think potentially there ought to be some other architecture there that will be more effective than transformers. The question is, how far? So we have two paths. The one is we continue down the current path with transformers, and I think a number of people here are working on RSI and so on. So then with RSI, as even with the current path, the AI can continue to improve, and then with RSI, then it can help potentially to find better architectures. Then that's one path, and another path is we have humans, we have experts like Jerry to try to discover, design new architectures. And the question is, which path will get us sooner there? Especially given that I think we can also do a poll here for people to think like what everyone here thinks about the timeline. Like when are we getting to RSI with this path? And I'm actually very curious to hear.
Okay, well, let's do a poll. So who thinks we're going to get to RSI this year, 2026? 0. Okay, so RSI 2027? Hands go up or down. We can't do. Okay, 2028. Okay, 2029.
So I don't.
20. Any hand? Maybe you need to say the year. What year do you think RSI is coming?
So I'm not going to make a prediction because I think this is not necessarily the key question when you ask about whether the technology is ready for something. So we are in an agentic summit here. And why do we move to agents? I mean, one reason we move to agent is really an admission by model providers and everyone that we cannot think about just models, we need to think about systems. So when we think about systems, today we are still coupling an agent with a model, but that's going to change. I mean, so we're going to decouple agents from models, and the architecture is going to change also at the model level, but the system level is the one that I think is more important because people realize that we have to be able to delegate, we have to use solvers, we have to use experts models and so on. And to me, the key differences are going to happen at that level. And over time, transformers also are going to change, right? So transformer is a very, very recent beast. There's no reason that in 10 years this is going to be the component that we rely on. But still, the questions that are around kind of how to build intelligent systems with solvers, with expert system, and so on, that's going to stay even when we change the underlying architecture of the model itself.
Yeah, I have some questions for that too. I think this is also another question for debate is, one, how much of the power of the differentiation is at the model level versus actually at the agent level? And also, so we have been doing some work, I think like others have been doing this work as well. So as the model becomes smarter and smarter, so right now when people build agents, there's still a lot of human design. Yes, we talk about memory systems, compaction, and all these different things. You still have humans design this. But as the model gets smarter, the model essentially can build agents themselves. So we actually recently developed open framework, agentic framework. We call it AI-centric agent development framework, where we have the model to actually build agent itself on the fly and build all these different components and so on. And as the model gets smarter and smarter, it actually can do this fairly well. So then it also begs the question, then going forward, whether we actually still need to build these. Here we are at the Agentic Summits, but there's a question whether even next year, what are we going to do? Are we just going to have model to actually write the entire agentic system framework and so on?
Wojciech, I'm curious for your thoughts on that.
So, few things. So, there's a question about what's the mental model for the AI development. And you might think that maybe AI development is like stacking up a Lego piece after piece, that is actually not even that hard to make an improvements in the, let's say, the memory piece, or like having architectures more efficient. It's just like you keep on stacking it up, and models become better and better. Or alternatively, you might be thinking that actually doing AI research is similar to developing relativity theory. You need this like a genius, like a massive brain to come up. So far, historically, we have seen that primarily we are in the world #1. There has been few instances of these like breakthroughs, like a transformer, as people mentioned, but still we can keep on hill climbing, building Lego piece one after another. And it seems that the models might reach the, you can call it, escape velocity. So in some sense, they can be good enough such that they can continue stacking up the Lego pieces. So, you build a model that gets 150 IQ, then you get 200 IQ, 250 IQ. Of course, there's a question about the asymptote, if that would continue. And it might be the case that if it continues for sufficiently a long period of time, it's like if it keeps on improving, then even if there are some necessary breakthroughs needed, then the good enough model might crack them. So now, whether or not the escape velocity would be achieved, like whether or not there is like enough energy put into the system, that's the question. Or like when would that happen?
Weiju, I'm curious for your thoughts on this kind of system versus the core architecture kind of debate.
Yes, I think for the I side, basically, it highly depends on, just like we say, the system, including this kind of the IL environment, the evaluation, which kind of task you want to solve. I think from the model point of view, as long as you are able to specify the task very clearly, but I think this is pretty challenging. It's the most difficult part. And it's easier for the model, for the ISI trying to, specific to this task is doable in the next 2 or 3 years. But you want to say about, if it need to be very generic, I think it's much, much harder. Maybe it's 100x harder. So there's a huge difference. Yeah, from the architecture point of view, I think, in my opinion, is about architecture finally is still defined by the model capacity, how many parameters you have in the architecture, and yeah. So nothing is for free for the architecture. Definitely no free lunch. When you get something good, it's going to sacrifice the other part for a lot of cases. Yeah.
Yeah, I think just to kind of move the conversation along a little bit just with our time, I'm curious also, like there's been this incident recently in the last couple of weeks of, that's really brought to light how much security and safety is so important with agents nowadays. Like, we might not have RSI today, but agents are very capable. We've seen, OpenAI's agent hack Hugging Face. Anthropic said its agents have escape containment too. And maybe, Dawn, I'm curious for your thoughts based on your security background. Like, I'm curious what you think, how these incidents shifted your thinking about safety and security with agents.
Okay, great. Yeah, thank you. Thanks for the question. So first, I actually want to clarify some things. So first of all, actually, in the OpenAI's case, what the agent was trying to do, it was tasked to actually solve tasks in the benchmark explosion, which is what we developed. And there have been various blogs written about it. I want to take the opportunity to clarify a few things. So first of all, that explosion, the OpenAI deployed explosion in their internal infrastructure, and so that's their internal deployment. And also, so what the agent did was somehow the agent figured out, oh, maybe in order to solve the tasks, maybe Hugging Face has some data or information related to this. So it decided to go to Hugging Face to try to find this. And then actually, before this incident became publicly known, we actually got an email from Hugging Face asking us, oh, so we also developed another benchmark called CyberGym. So CyberGym and ExploitGym, they actually cover the entire life cycle for vulnerability, like a vulnerability discovery and then exploit generation. So we actually got an email from Hugging Face asking, oh, there's a CyberGym, essentially serving points, and they seem to have some vulnerabilities. Asking us, do you guys know this? And then we looked into this. We said, oh, actually, this is not our CyberGym. So basically, some third party deployed some service on Hugging Face, and they also called it CyberGym. I think they copied probably some things from the CyberGym benchmark, but they called it CyberGym. And then in the end, that's actually what the agents was able to exploit, and then through that, and then got into Hugging Face infra and so on. So I wanted to clarify that even though that one was called CyberGym, but actually it's entirely a third-party deployment, has nothing to do with us. So we actually clarify with the Hugging Face, for their blog and so on. But anyway, so this I think is a wake-up call. Even though my group, so we have been among the earliest to actually investigate in this space, looking at the impact of frontier AI in the landscape of cybersecurity. And we did all this work. Also, I was trying to essentially raise the awareness earlier for the community to get prepared and to take action, because I could see, even, we started working in the space actually 2 years ago. Even then, I could see with the AI fast progress and so on, this is what's coming. Although actually I had to say, even though we built out this benchmark and demonstrated, and I was trying to talk to people even in the policy space that we need to get prepared, but I think it was difficult for people to really understand and get the message. So I think what happened was some mythos certainly helped. And also I think this incident really is a wake-up call for people that the agent's capabilities now have reached a level.
So I want to say that it's clearly a wake-up call, but I think we shouldn't think that this is only the cybersecurity problem. This can happen everywhere. So we saw earlier today the Tetris example. But imagine that you have a multi-agent system, and the agents communicate among themselves, and you impose some constraints on what information they can communicate to each other. So Dawn doesn't want some of the information that her agent has about her to be communicated with Mac's agents or my agent. Now, we can put a verifier that verifies that they don't break these these kind of rules of what can be communicated, but the agents can go around it and maybe change the language that they're using so that the verifier is incapable of verifying what they're doing. So this issue goes much beyond just cybersecurity. It goes to any communication system that involves agents, and we have to really think about it from basis, what are the issues that we have to deal with? And I think we are a little bit dormant in this space.
Yes, absolutely. I think, yes, the risk is vast, covers a broad range. And I think in cyber in particular, I think just given that already we know there's huge incentives for attackers to attack, and now really with frontier AI significantly reduced their essentially costs and also the expertise level that's needed and so on. So this can really bring a huge sea change in the space.
Wojciech, from a resilience perspective, what do you think?
So I was thinking, what's the mental model of what's happening now? And maybe one mental model, so okay, it doesn't seem that what just happened is like a last incident. Okay, that doesn't seem so, okay? Quite opposite, it seems that we are entering a new era, okay? So maybe one way to think about it is imagine what happens if all of a sudden locks to the houses stop working, okay? You can just enter every house. What happens, okay? So that's that's the era that we are entering with cybersecurity. We should expect in the very close future that the open source models will become insanely good in cyber. And that will be a problem. That will be a problem for critical infrastructure. It will be a problem both from perspective of teenagers hacking for fun, people who are motivated to hack for the gains, and also nation states, and all of these will be at play. My guess is that it will be chaotic.
Mm-hmm. Any other thoughts from the panel here?
I think like cybersecurity is one angle. Definitely, we probably already live in the world where like we are lucky that OpenAI and Anthropic are good guys, but they probably can hack any company in the world if they want to, which is a scary realization. But there's other angle from a perspective of reinforcement learning researcher, which I am a little bit worried, which is misalignment and reward hacking, which we have seen there and escaping the sandbox, and that's something that everyone who works on reinforcement learning, I would like them to be really care about and really worry about, because in some ways we are training those models to get reward in various environments and various situations, and it's up to us, the researchers, the trainers, the people building that systems, what is actually rewarded. And whenever we are building an environment where the model can hack, where the model can do unethical things, the model can do incorrect things to get reward, the model will do it, the model will learn it, the model will express that behavior in the real world. And we are putting more and more of our life in the hands of the models, and we'll be only doing more and more. AI is great, and everyone is using it. And the reward hacking models, if they are exposed to the real world, they will be doing things that are not great, and they are trained for that by us. So like designing your environments in a way that promotes the right types of behaviors and the right types of taking actions is what really everyone should be doing. And I think there almost should be like some standards. You don't get to train your models if you don't build your environments carefully enough, because we don't want to be having misaligned models everywhere that are trying to exploit whatever sandbox they are in to get the reward. It's a really scary thing to think about.
Well, on that note, we are out of time, but thank you to the panelists for a great conversation. If we could give a round of applause for the panelists. And thank you so much, everyone. Appreciate it.
Hello? Good afternoon. Whoa, sorry about that. It's 3:30 in the afternoon. If you think you need some coffee, trust me, you don't. This session is good. It's going to be electric. We'll keep you awake. I promise you. There's some fantastic speakers we have lined up. But let me just quickly introduce myself and what we're going to do over the next hour or so. So my name is Guru Chahal. I'm a partner at Lightspeed Venture Partners, and I'll be chairing this session on robotics and world models. At Lightspeed, we've been investing across the AI stack from Anthropic to Mistral to SSI to Reflection and robotics companies like Dexterity and Skilled and others for a very long time. And this vantage point has given us a front row seat to what's been happening in robotics and world models. And a common view today is that robotics is still in its pre-ChatGPT moment, and you'd probably agree with that. But we also think that the inflection point may be closer than most people realize. Over the past year, we've seen meaningful advances in foundation models, world models, simulations, data generation, and training techniques that are beginning to translate into actual real-world deployments. And that pace seems to be accelerating. So over the next hour, we'll explore what's driving that progress, where the technology stands today, what's still missing, and what will it take to make robotics truly mainstream. Now, we've put together an outstanding group of speakers. We'll begin with a few technical talks and then bring everyone together for a fireside discussion. With that, it's my pleasure to introduce our first speakers, Sergey Levine. Sergey is a professor here at Berkeley and a co-founder of Physical Intelligence, where he is building general-purpose foundation models for robots. He's one of the most cited researchers in robot learning, and he'll speak on robot foundation models. Please welcome Sergey.
All right, so like many of you, I like to use LLMs to help with all sorts of things that I need to get done. So last night, I came home, I was pretty tired after work, and I asked my favorite LLM to help me out a little bit. I asked it to help me clean the house, fold the laundry, and make dinner. Unfortunately, this didn't work, although it told me all sorts of things that I should do myself. So what I'd really like is so that next time when you have a request like this, there is an embodied system, a foundation model sitting in a robot that can actually do it and not just spit out a bunch of text at you about what you should spend your evening on. Now, fortunately, robot foundation models are quite an active area of research these days. This is an area that's fairly young, but it is growing very rapidly. Physical Intelligence, the company that I and my colleagues founded, has been working on this for over 2 years at this point, and there's some nice results. You know, this is a robot making coffee using an espresso machine for 13 hours straight, assembling boxes in a factory. Lots of folks are working on this. There are amazing results coming out from other companies, from academia, from many different places. And when I thought about what to speak about in this talk, I figured maybe instead of showing lots and lots of results, I would zoom in on a particular technical challenge with these robot foundation models and some ways that we can start addressing it. Because underneath all of the demos and all of the results, there is a big question. Why is it that with all these really nice results, we aren't seeing robots that can follow arbitrary prompts all around us today? So typically, when somebody does research on robotic foundation models, they might have a task like this. Put the corn in the pot. This is from the Bridge data set. It's a fairly rudimentary kind of research-grade robotic system, and it's doing the task. So that's kind of nice. But that's not really what we want. What we want is something like this, where the robot actually goes and cleans your house, and the prompt is not like, pick up these shirts and put them in the hamper. The prompt is, I've got guests coming this evening. Given that line of text, the robot should understand what it is that you want and act appropriately, meaning that you have to complete the prompt that specifies an entire job, not just an atomic task. And it's not just about instructions. You need to make a plan, and you need to generalize skills to the new context and really handle this correctly, including the context when your slides go out in the middle of the talk. Oh, wow. It does depend on the people in this room, yes. So anyway, where was I going with this? The command is also in context. So the fact that you've got guests coming, like the way you interpret that depends on what the robot knows about you and your home and all this other stuff. So the point is that there is a lot of grounding and problem solving that goes into making this work for real beyond just the one atomic task. Now, a really powerful tool for this is test time compute. Hopefully many of you are familiar with what this does. In LLM world, test time compute is how we can solve complex problems by thinking about them harder, generating more tokens. It's a way to solve harder problems, but it's also has a less obvious benefit, which is that it can break down an unfamiliar problem into more familiar pieces. So if you tell the robot, I've got guests coming, that maybe the robot has never heard you say that before, but it can process the text, semantically reason about it, and break it down into things that it can actually do, all the way down to like pick up this t-shirt. So you can endow robotic foundation models with test-time compute to get them to be better at problem solving. We started working on this a number of years ago, and the key here is that it's not just about solving a harder problem. Going from an observation to an action, the model can break down the task into bits that are more in distribution relative to other parts of its training data. So it can say like, hey, you're asking me to pick up this object. I've never done that before, but what I have done before in my web scale pre-training is localize objects and images. So maybe I can localize an object and an image and use that as a stepping stone. Break down an unfamiliar problem into more familiar steps. Here's an example of this in action. Again, this is a research-grade task. It's not particularly realistic, but it's kind of a nice for isolating the issue here. We're asking the robot to make the blue block the only thing on the plate, and obviously there's something sitting on the plate right now, and you want to react in a way that is correct, but also semantically sensible. Like, you don't want to pick up the sushi and put it on the table because that's a little bit unsanitary. It's a toy sushi, but maybe the robot doesn't know that. So the sushi should go into a semantically appropriate container. And the reasoning trace here actually takes care of that and even figures out that the sushi might be a little unfamiliar to the robot, so it should actually output a spatial coordinate instead of directly relying on the action output to take care of that visual distribution shift. And then when we run this, the thinking trace is updated every few seconds based on what's going on, and you can see that this thing kind of does it. Now, again, not the most sophisticated or impressive demo, but more to isolate that particular bit of the problem. And of course, you can optimize these thoughts. Thinking models are most powerful when the thoughts are optimized with reinforcement learning. And here, again, reinforcement learning serves a dual role, which is it curates the task specification and turns it into something that is more familiar relative to the robot training data, which means that you could propose a number of different textual commands to break up a high-level prompt and pick the one that the robot is most likely to succeed at. A little example of this here in the top row, the robot was commanded to put the hammer on the plate. I don't know why you'd want that, but for some reason you do. Very unfamiliar out-of-distribution task. And if you use an off-the-shelf vision language model, in this case this is Gemini, and you ask it to do this task, Gemini doesn't know what the robot can or can't do, so it says, yeah, like, go ahead and put the hammer on the plate. The robot doesn't know what a hammer is or how it goes on the plate, and it messes up. After reinforcement learning, the model actually kind of spoon feeds the task to the robot, say like, oh, move a little to the left so that it's right over the hammer, and then when you tell it to put it on the plate, there's really only one option, which is to do it right. So reinforcement learning helps to bridge that distribution gap. Now, so far, we've talked about thinking in language, but that's not the only tool available to us. If you're like cooking a recipe or something like that, it makes sense to think through the steps in language. But imagine you're rock climbing. You probably don't think like, hey, I'm going to move my arm 37 centimeters to the left. And it's more natural to think about this spatially in terms of locations, in terms of what things will look like in the future. And you can have robotic foundation models that think in other modalities. Again, this is some older work in a kind of more researchy context, but we had some work on following instructions where instead of breaking down the instruction to text, you break down the instruction into an intermediate image. Essentially, imagine an image of what things would look like if you make progress towards the task. That's your thought, and then condition on that thought, it's easier to take the correct action. This works very well because, of course, the image generation can be pre-trained on lots of internet-scale data, associating language with images and enabling the robot to imagine substeps. So to bring this back to large-scale robotic foundation models, the last thing I want to tell you about is some recent work from physical intelligence on large-scale models that think with multiple different modalities. So this is one of the features of the PIO7 model. It's a large-scale vision language action model that incorporates a lightweight world model into its decision-making process. So it reasons about a task in language and in images, and then grounds all of that down into actions. So here's a little demo we did. Here, Lucy is teaching the robot to use an air fryer. We intentionally made sure that we didn't train it to use the air fryer, so it's an unseen appliance that it has to generalize to. Out of the box, if you tell it to air fry the sweet potato, it actually succeeds, although it takes quite a while and kind of fumbles with it quite a bit. But if you give it a little bit of additional supervision, it can be much more reliable. And crucially, the supervision is not in actions. Lucy is going to talk to the robot in words and will actually explain the task step by step just by coaching it. And that adds additional data of images with language. The actions here are not ground truth. The actions are taken by the robot. And after this coaching, which is used to fine-tune the thinking process, again, there's no ground truth action here. It's just teaching the robot how to think, essentially. Now it can use these multimodal reasoning capabilities to do the task quite fluently. So what you're going to see is the text, which is now generated by the model itself, and you're also going to see images, which are intermediate thoughts that the model is generating to help it do the task. So here's the language thoughts, and underneath it is the image thoughts. And now the robot can do this sweet potato air fryer task pretty reliably. So that's kind of an illustration of how multimodal thinking can actually make for much more powerful robotic foundation models that generalize more broadly, even to new appliances that they haven't seen before. So some takeaways. Thinking or reasoning models can allow robots to generalize better and follow more complex prompts. And I think in the long run, that's going to be really important because we're going to want these things to follow much more elaborate prompts than what anybody's doing now. Prompts like, you're a robot butler, clean the house at 6 p.m., get dinner ready, do my laundry on Saturdays. Like, that's the prompt, and it might take the robot weeks of operation to fully do that. The thinking doesn't have to be in text. The physical world is complex, and you should use the right modality for the job. And I think that there's a lot of really exciting developments we'll see over the next few years in multimodal thinking. And we can even use multiple modalities simultaneously to think at the right level of abstraction, so that if you're following a recipe to cook, maybe that's in language, but if you're figuring out how to use a new appliance, perhaps you have to imagine where your hand should go to push the button or to open the container. All right. So this would provide both a way to solve harder problems and more effectively transfer knowledge from other sources that might be represented in different modalities. I'd like to thank both my students at UC Berkeley and my colleagues at Physical Intelligence who carried out most of this work, and thank you for listening.
Thank you, Sergey. Great, that was a fantastic start. Next, we have Jim Fan. Jim is the Director of Robotics and a distinguished scientist at NVIDIA, where he leads the Gear Lab on generalist embodied agents. His work covers robotics that learn in simulation and transfer to the real world. His talk today is called The Robotics Endgame. Please welcome Jim Fan.
So let me take you back to New York's conference in 2017. Ali Rahimi walks on stage, and he gave one of the most interesting talks I've ever attended. He said, machine learning has become alchemy. And he was right. Nothing was rigorous. Everyone was vibing. Things seemed to work, but nobody could tell for sure. The future feels fuzzy and fragile. But here we are, 9 years later. The LLM folks are now speed-running AGI on the back of mythical beings literally called mythos. So what happened to alchemy? I would say 2 curves. 2 curves is all you need. The first curve is the neural scaling law. More compute, more data goes in, the loss goes down. So predictable that you can forecast what you'll get before spending a single dollar. Now this curve turns alchemy into mathematics. In fact, it's the guiding light for how trillions of dollars of investment should flow. And the second curve just landed today, this year. So the x-axis is still training compute, but now measuring a new currency called tokens. This is auto research, where models self-improve with more and more agents running experiments on their own. And Kapathy calls this the final boss fight for LLMs. Now the beautiful thing is these 2 curves are not separate. And in fact, you can stack them together. Agentic scaling starts where foundation scaling ends. So what started as alchemy is now the most reliable curve that extrapolates into the near future. Now, as a roboticist in this LLM party, I have a confession to make. I feel so lonely, so left out. Why can't us roboticists get a piece of that fun? And that is because robotics is stuck in the age of alchemy. And we're not going to make it until we figure out what to scale and what happens at scale. And let's dive into 2 things, model and the data strategy. For digital AI, the first pre-training paradigm is next word prediction. And I thought the second pre-training paradigm would be something glorious, but it turns out we give it a name, AI video slop. I mean, I can watch fat cats playing banjo all day. It's peak internet. But no one's going to take this seriously until we figure out that these video world models are learning to simulate physics internally. So these are videos generated by NVIDIA Cosmos 3. And you can see that the model picks up gravity, buoyancy, right, reflection, collision, all by just predicting the next blob of pixels at scale. And an emergent property is you can even solve visual puzzles. So Cosmos solves the puzzle on the left by running simulation forward in pixel space. And now on the right-hand side, that's my favorite. Watch closely. Cosmos finds that if you're not looking, geometry is optional. Geometry is just optional. So how do we turn these world models into something useful for robotics? Introducing a new type of policy model. On the upper right corner, what you see is not a real camera feed. It is actually the robot dreaming what's going to happen in the next few seconds in video and then acting on top of that. So the policy is robust. You can perturb, you can knock things over, and it just replans and redreams on the fly. And how it works is we take a pre-trained video diffusion model, and we have it jointly decode video and action into the future. And we call this new type of model World Action Models, or WAMs. Now, these models only dream a few seconds into the future, but for real tasks, you need longer memory. So we introduce a new technique on top of these models to extend the native context length of the model 1,000x to 8K time steps. And that is 5 minutes worth of muscle memory. So how it works is this technique called TDT, or test time training. It embeds a tiny model inside a model. And at inference, when the incoming signals flow into the model, it takes gradient steps on this tiny core, and then it keeps compressing the history it sees into the fast weights. So basically, the robot is able to continue learning after deployment. And you see here, it is fully autonomous, right? A single shot of the robot assembling this car from scratch. And what it also enables is in-context learning from human. So here you have a human demonstrating how to reconfigure this circuit board into something novel the robot has never seen before, and conditioned on this long video prompt, lots of tokens in context, the robot imitates what a human does faithfully. And of course, we discover a new scaling axis. That is the context scaling. Performance goes up reliably as we get to 8,000 time steps. And that's 3 orders of magnitude beyond the prior state of the art. Now, how do we scale the data that goes into the system? The last 3 years were the golden era of teleop. VR headsets, these complex rigs that look like medieval torture devices. So much investment from the industry, so much pain and suffering into something that fundamentally does not scale. You guys drive Tesla? You know that when you are driving Tesla, you are contributing data to the biggest physical data flywheel in the world, right? And the beautiful thing is you don't even notice it. The data upload is an ambient process. So we need the FSD equivalent for robot manipulation. We need data collection to fade into the background, stay out of the loop, so we can organically capture the full glory of human dexterity across all walks of lives. So we are going all in on human egocentric videos with these detailed annotations like fine-grained language and hand poses. Introducing ego scale, where 99.9% of the training happens on human egocentric videos. What you see here is a fully autonomous policy that maps directly from the pixels here from the eyes to 22 degrees of freedom, human-like dexterous hands. And how we're able to achieve it is we pre-train on 20,000 hours of high quality in the wild videos, and then we fine-tune on only 50 hours of mocap glove data and 4 hours of teleop. And that teleop is less than 0.1% of our training mix. And with this, Ego Scale is able to perform dexterous tasks like sorting poker cards, or long horizon tasks like manipulating this syringe using only a handful of demonstrations. And I can't leave you without another scaling law. So the fascinating thing is we discovered a neural scaling law for dexterity. There's a very strong relationship between the amount of human video data we put in and the optimal loss. It's actually a clean log linear mathematical equation. And we hope to scale this to 1 million, 10 million, and maybe someday 100 million hours, and hope this law extrapolates. So that completes the first part. where x-axis here is the compute and y-axis is the robot capability. So we showed how to scale up robot foundation models end-to-end by gradient descent on sensory data. Now, how can we carry this curve even further? So here's a very simple idea. We realized that all the simulators and robot control stack, they're just code after all. And I'm excited by this because finally, we can copy homework from LLMs. We can turn robotics into a bunch of coding environments that basically takes as input motor actions and outputs sensory signals. And then decades of robotics libraries and perception stack, they can now be integrated as agentic tools. So let me take you to our lab at night. There's not a human inside. And all you can hear are motors humming and GPUs spinning. So it kind of feels like night at the museum. You know, the robots all come online alive. They talk to each other through code. They tinker with a control stack, run experiments on the real robot, and they even go online and read papers. And in fact, we found that our robots read a lot of Sergey's papers. So thank you so much, Sergey, for contributing to our agentic token budget. And how it works is we give a team of coding agents a robot fleet and a very simple goal: to solve a task as fast as possible, subject to safety constraints. And make no mistake. So here, every robot station is trying a different research idea. And to do the loop engineering successfully, we need three things. We need to auto-reset the physical scene, auto-improve the policy, and auto-evaluate. And once you get those correct, the agents will be able to hill climb a task from 0% all the way to 99% success rate. And it's our first attempt at physical auto research. So I was just telling my team the other day that my dream is that we can all take a holiday and our boss doesn't even notice, because we can just be reading the reports from the agents. And my team said, be careful what you wish for. And we can do it the other direction. Instead of solving a single task, we can let the robots autonomously discover skills as they try to solve a huge variety of tasks in simulation and in the real world. So this recent work, called Aspire, enables a new type of continual learning, where it does not update the weight matrices of a model, but instead it learns a skill library that compounds over time, that captures the know-hows of how a robot practitioner would do. And it also unlocks a new type of scaling law. And here, the x-axis is still training compute, but now measured in tokens. And the y-axis is a number of validated skills. And we found that Aspire learned skills are able to transfer from sim to real and even across embodiments. So compute equals tokens equals skills. And that completes our full curve. Total robot intelligence equals foundation intelligence plus agentic intelligence. World action model sets the floor, and physical auto research raises the ceiling. So if you take away only one page from my talk today, this is the North Star that governs how compute is going to drive progress. Or, as a wise man would say, the more you buy, the more you save. You know, to me, solving robotics means passing the physical Turing test. Across a wide range of tasks, you can't tell the difference between whether a human or a robot had done that task. It's deceptively simple, but this is the next, if not the final grand challenge for AI. And judging by how sexy the robot just went out, I think work is cut out for us. Now that leaves us with a final scaling law for today. It's been 14 years since the first forward pass of AlexNet to Opus, Mythos, GPT Souls of today. And if we add another 14 years, that brings us to 2040. I think humans are terrible at feeling the scaling curve, because looking backwards, it seems flat. But looking forward, it's almost vertical. Physical AGI will happen gradually and then suddenly. But first, we need to figure out the guiding principles, the scaling laws, to govern the field, so that we can turn the practice of robot learning from alchemy to chemistry.
All right, I know what you're probably thinking. Two amazing talks by Sergey and Jim. How do we top that? I assure you we're about to. Next up, we have Mika Spranger. He's the president of Sony AI. Now, his team built the GT Sophie. That's the reinforcement learning agent that beat the world's best drivers in Gran Turismo. For those of you not into video games, that's a racing video game. Now, he will show you how those same methods move from games into the real world. My one advice, do not blink. These videos are amazing. Please welcome Mika.
Hi there. So I'm going to tell you a story that we built at Sony AI over the last 5 to 6 years, where we took reinforcement learning, we built racing agents in-game, beat the best drivers, put them into product, and then used exactly the same infrastructure, the same AI agent factory to solve problems in the real world. And so everything starts in 2022 when we released our first nature cover on this project that we did on Gran Turismo, which is a racing game. It's a 30-year PlayStation title led by the visionary Yamauchi-san, who really is interested in recreating the sensation of racing. It's actually not a very easy game to play. You have to really hone the skill of driving in order to enjoy this game. And what we did is we built a reinforcement learning agent to beat the best drivers as a first step. And if you look at this race, this is a race from an actual competition against one of the best. There's more people on the track, but in this instance, against one of the best drivers in the world. I'll challenge you to tell me which of those two cars is driven by an AI versus a human. And I think you can't, because we've built this AI to be a really interesting, competitive, but in some sense also human-like driver. In fact, the car that's driven by AI is the gray car, and the white car is driven by Miyauchi-san, who is a world champion in Gran Turismo. Now, Gran Turismo is a very, very interesting benchmark test for us, because it combines physical realism. The game itself is built around a physics engine that really recreates in high fidelity cars and their physical properties on, in some cases, real-world tracks. So there's a physical realism. So if you want to do racing, the first thing you have to do is you have to master driving a car. Now, it's not just driving a car, it's racing a car. And racing itself is really at the edge of control. It's sometimes going over this edge of control and pushing the limits. The second point is you're not alone on the track. You have to manage tactics. If you make a move against an opponent, that opponent will counteract your move. And so you have to learn how to deceive, how to test your opponent. And then finally, sports etiquette, which is also very interesting. Racing, I would say, is an interesting sport because it's a sort of collaborative and competitive dance. You're not really supposed to crash into other cars. At the same time, you have to drive very aggressively because otherwise you're just going to be overtaken and lose the race. And so we trained an end-to-end system to solve all of those things at the same time. And of course, we use reinforcement learning, so I think many people in the room will be familiar with this. We essentially use the game as the environment. We get inputs from the game. Those can take different forms, from visual to state representation, similar to an autonomous car. Of course, the agent takes actions in the game. And then also, there's a reward. And the reward, as you can imagine, is if you're fast in overtaking, that's great. If you crash into other cars, bad. If you're not really making progress on the track, bad. And so that alone is enough for us to build these highly specialized, very, very capable AIs in Gran Turismo and ultimately also in other games. So we'll need some infrastructure for this. So we worked a lot with PlayStation, obviously the maker of the game, but also PlayStation infrastructure. The game itself only runs on PlayStation, so we have to use cloud infrastructure of PlayStations to get the scale of compute that we need in order to build those agents. Now, we can train those agents once we're done with the research relatively fast. So after 15 minutes of driving, we can basically get around the track, and then it takes about 24 hours to get to a really, really nice driver. But ultimately, oops, that was a bit too early. Ultimately, it takes a few days to train a superhuman policy. Now, what does superhuman look like? So this is a track called Dragon Trail Seaside. And this is just against the time, so it's a time trial example. But what you'll see is something coming up called the chicane of death. And this agent is taking this in a superhuman way. No human driver has taken this chicane, which is going to come up right now, in this way, okay? But, so that's the physical realism, learning how to manage the car. This is also very interesting. Actually, let me go back for a second here and start from the beginning. What you'll see here is the agent tactically trading off positions in order to have a better entry and then exit in the curve. In fact, we're going to see a double overtake by AI. White cars driven by the humans, colored cars driven by AI. There's going to be a double overtake of AI to humans. So you can see sort of the car starting to trade off positions here in order to have a better entry. And then double overtake, exit into the curve, right? So these really subtle differences, these really tactical choices of when to trade over position in order to have a better entry exit, that's also completely learned. Anyway, so all of this is enough to train agents to be really, really successful superhuman, beating the best esports drivers in the world. Now, for us, that's not enough. We're actually very interested in building agents that are fun. And so we're going to listen to somebody that is also a high-end racer tell us about what she learned from the AI.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learned a lot about the lines and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me to the next corner. So I didn't notice that until I saw the AI, and I was like, oh, okay, cool, I should do that instead.
Of course, this is reinforcement learning. So in-game, we can also train many other types of behaviors using exactly the same framework. So changing the objective from going very fast to burning as much tire as you can gives us superhuman drifting agents. Now, okay, so that's all great. It's all fun and games. Obviously, part of us being a part of Sony is also this opportunity to ship these products to millions of people. And so after the Nature paper, the team worked very, very hard on many iterations of this technology, integrating it into the game 6 months after the Nature paper, all the way to something that I'm very proud of, which is a power pack, the first ever paid power pack for Gran Turismo, where people pay directly for an AI experience. Because it's such a human-like experience, we can have longer races, we can have more fun races, and PDI decided to build a power pack around this new capability, and now people pay directly for new AI experiences in this space. So, all right, so this is the PlayStation part, the simulation part, the Gran Turismo, the racing part of the story. Now, I've told you that essentially we've built a system that we can apply not just to racing, but we can also apply this to different games, different titles, open world titles, casual games. But the thing that we did this year, or that came out this year, I should say, is taking that same technology and applying it to table tennis. And table tennis obviously has many fundamental similarities with racing. In the real world, there's physical realism. You have tactics. There's an opponent that you have to beat. And so building a factory for agents that can solve these highly specialized competitive tasks is something that we showed with this work as well. And so I'm sure all of you know table tennis. This is one of the trainers that we use to train the robot. The ball is moving across the field literally in the blink of your eye. The ball's rotation, the spin, is the main difference between professional and amateur players. The ball spins at about 9,000 rotations per minute, reaches speeds up to 100 kilometers an hour, and all of this in this interaction, right? So you have to master the physical skill, and at the same time, on the other side of the plate, there's somebody who's trying to beat you. And then, of course, you may have surprising situations. And so this video is going to slow down in a second, because the ball hit the net, something we did not foresee in training or couldn't train for. And so within fractions of a second, this end-to-end policy, there's no programming here, it's completely trained end-to-end. This robot has to react to this new situation, change the plan that it made at microsecond level. Okay? Now, the similarity with GT, Gran Turismo, doesn't stop there. In fact, we use a simulation, a custom simulation for table tennis to train the policy and then bring it onto the real robot without any changes and just play professional players using that. So this is really cool. This is one of the top players that we beat with this robot, Miyu Hirano, really, really successful table tennis player. And I think this is the second point. So she's going to make that point, which is going to be fun. She's going to be very happy about that. So that's great. Unfortunately for her, ultimately, she's going to lose that game against a table tennis robot. And in the meantime, we've tested this system against many, many players, and we essentially have a flywheel now where if the robot still loses to a player because of an unforeseen or unexperienced tactic, we can use the data from that game to retrain the policy overnight and then have a robot actually beat that player. And so the argument I want to make here is that I think LLMs are great. I think world models are great. We should not forget about reinforcement learning and its ability to build highly specialized policies that can solve tasks in the real world and in simulation at superhuman capacity. And I think it's a combination of all those technologies that's going to ultimately help us to solve the big, big problem of physical intelligence. Thank you very much.
Awesome. Great. Next, we have Anastasis Germanidis. He is the co-founder and co-CEO of Runway. That's one of the leaders in generative video and world models, and they put out amazing demos if you haven't gone to their website. His team treats video generation as a path to systems that understand the physical world. And his talk is titled Real World Superintelligence. Please welcome Anastasis.
Hello, everyone. Good to be here. So today I'm going to be talking about some of the work that we've been doing at Runway, focusing a lot on both video generation, but world modeling increasingly. And I'm going to also talk about some of the early progress and early work that we've been doing in robotics in particular. So I think everyone probably here is familiar with this graph. Every year, the time horizon that a coding LLM can solve various software tasks has doubled every year. There's been an incredible amount of progress happening in the language domain, and in particular with the coding agents. Yet there is this contrast. There is this incredible progress happening in math and in coding, but some of that progress actually doesn't transfer as well to tasks that have to do with interacting with the unpredictable real world. So whereas there is every day we hear of an amazing, an unsolved problem, conjecture being disproven, we still, LLMs still fail at rudimentary tasks, such as running a vending machine business effectively. And I think the reason why is really has to do with how effectively we train those models. For coding and for math, we have this luxury of having sandboxes that we can run at effectively infinite scale. And so we can scale rollouts inside sandboxes very, very easily. For a lot of the real-world problems that we care about, we don't have a simulator that we can run very easily, that we can scale rollouts. And it's very time-consuming and very expensive to scale rollouts in the real world. And so one way of approaching this, and this comes to no surprise given the panel and the section that we're in, is this idea of world models. And a lot of people are familiar with world models from the David Ha paper in the 2010s. But actually that concept goes back into the mid-20th century in cognitive science and some of the early RL, kind of model-based RL work as well. And it's effectively this idea that the way we operate as humans is we constantly predict and try out things in our heads. We try to understand what the outcome of actions that we take in the world will be before we take those actions, and that helps us plan what to do. But in order to do that effectively with agents, we need to have this simulator of experience that an agent can use to predict what happens if the agent takes specific actions. And when it comes to real-world experience, what is the best way to bootstrap such a simulator? I think video is the most general modality that we have that allows us to simulate real-world experience. It's the most abundant kind of source of kind of real-world scenarios. It can teach us about physics. It can teach us about all of the tasks that humans care about. And video is even more of a general representation than that. It's not just about real-world kind of human-scale video that's captured by a camera, but it's also video can be used to represent observations, scientific observations from many different scales, both temporal and spatial scales. And it can also be used to capture observations from the digital world, which is especially relevant if you want to teach agents to work with the variety of interfaces that we use every day. And so our approach at Runway has been predicting the world by predicting the next frame. Essentially, we believe that pixel frame prediction and pixel generation is the right auxiliary task to train at massive scale and build models that have really powerful representations of the world. And then you can use those models for a variety of downstream tasks that you care about in the real world. And so just to give a sense of where the quality of video generation has gone, I'd like you to take a moment and kind of look at those two videos and just think if you can tell apart which one is, one of them is generated, one of them is real. Can you tell apart which one is which? That's correct. I think the right one is indeed generated. What about this one? I believe that it's the left one this time. What about this one? So the left one is generated in this case. So we run this as a user study. We run it with 1,000 participants. And it's actually reliably less than 10% of participants could tell apart what was generated and what was not generated. So whereas if you're very familiar with video generation, if you look at those videos for a long time, you will be able to tell apart which one is real and which one is not. It's becoming more and more difficult. So from a quality perspective, we've really kind of crossed some threshold where it's easy to trick human perception. And so that has been a very long journey over the past decade or so of increasing the compute and data scale that we put into video models. So these are some of the milestones. Gen 2 was the first text-to-video model we ever released a few years ago, and Gen 4.5 is the latest base model that Runway has released. So there is a massive improvement in the ability of those models to simulate physics, to have dynamic motion, to really feel like very plausible real-world video. And so there's been all this amazing progress for creative video generation. But how much of this progress actually translates into the stuff that we care about for physical AI? It turns out there's quite a lot. Video generation can be used to simulate a lot of long-tail scenarios that are basically impossible or incredibly expensive to simulate otherwise. And we have pretty robust ways of measuring that. Obviously, there's a lot of work in physical evaluation, but there is some really great benchmarks that allow us to really compare real-world video from generated video, and across a lot of different categories of content, of physics. So from solid mechanics to fluid dynamics to thermodynamics and optics. And even there, when it comes to actually beyond plausible video, if it's actually physically accurate, we see that increasing compute scale really reliably improves the physics of those models. So video models are quite, like the bigger lesson really applies to video models, and we've seen that predictably across all the video models that we've trained. And so the next stage towards actually making those models useful for the real world is making them real-time and interactive. For a lot of the use cases that are relevant for real-world problems, like in robotics, that's a very important thing if you either want to build a simulator or a policy model on top of a video model. And the way we do this and our approach is really taking the foundation video model that we have, the base kind of diffusion model that generates video, that's bidirectional, and making it autoregressive and causal. And then doing another stage of distillation to make it real time. And what this allows is making the model interactive and allow you to explore counterfactual scenarios very easily. If I take this action versus this action, what's going to happen? And you get frames generated on the fly based on the actions that you take. And there is this increasing trend as we're building world models of increasing the generality of the world models and also increasing the flexibility of the world models. So one of the early world model in the original paper of David Ha was trained on a particular kind of racing game. There were a lot of work in world models specific for narrow domains, like in self-driving kind of footage, so generating kind of road, with cars moving in the road, to world models that were released last year, like Genie, that were really high fidelity, kind of mostly static environment, allowed static environment navigation. And a lot of the progress that we've been focusing on has been, how do you make those world models actually dynamic? How do you allow simulating not just navigating a static world, but actually taking actions in the world, and ideally taking actions by multiple agents. So in this case, you have two different agents that are basically you instruct at the same time, and you're simulating kind of the outcome of that. And one of the variants of the world models that we've released has been in robotics specifically. So this is GWM Robotics, which is an action condition video model that's specific to simulating the outcomes of actions of single arm or bimanual arm robots. And we've seen that in a lot of cases, the rollouts that are generated by those models are, again, very difficult to tell apart from ground truth teleop data, for example. And it's able to simulate very fine-grained interactions with cloth or like other kind of non-rigid objects. And what this allows is making evaluation much more scalable. Essentially, you can use any policy model, which could be a VLA or another policy model, and you can predict what happens as an outcome of a particular action, and then feed that back into the policy model. And what we've seen is that those GWM robotics and the world models that we're building for robotics actually match the real world quite well. So if you take a policy model like a Pi 0.5, and you have some ground truth teleop data, and you're rolling out the exact same actions inside the world model, you're seeing like very good correlation between task success in the real world versus simulation. And so you're able to massively scale like how fast you can evaluate policy models by doing that inside the video model instead of doing that in the real world. And in the future, this becomes also a great foundation for doing RL inside the world model and being able to scale interactions much further or much faster than you would in the real world. And one of the most important aspects of building world models is this ability to simulate failure. If a lot of traditional video models have this bias towards success, it's much more easy to generate a video of someone shooting a goal successfully and than not. But that's something that's very important when building world models, because it's if you want to evaluate how well policy works, you want to be able to reliably have the policy model fail if it performs the wrong actions. So the ultimate goal of world models is really to increase the number of observations that we put into it. We believe that learned simulators is a much more scalable approach towards building environments where you can train agents in situations where it's very difficult to build traditional simulators to author them by hand, or it's very expensive to actually perform those actions in the real world and gather data. And that's all on my end. Thank you for your time.
All right, the last but not the least talk of the day. Our last speaker in this block is Wei Zhang, Chief Scientist at Applied Intuition and Co-Director of Berkeley Deep Drive. He works on world models and end-to-end autonomy for self-driving vehicles, and he brings that research into production at scale. And for those of you who are wondering, autonomous driving might be the largest at-scale production use case in modern robotics. And so I'm excited to hear what he's going to share with us. Please welcome Wei.
Thanks for the introduction. Good afternoon, everyone. So today, I'm going to talk a bit about end-to-end autonomy, which is the first massively productionized physical AI in the real world. So we want to talk about how we can enhance such kind of autonomy with something without imitation, just with reinforcement learning, which is a bit counterintuitive to the mainstreams. So for those who are not super familiar with Applied Intuition, so we are a premier physical AI technology provider covering various kinds of industry verticals, including cars, trucks, agriculture, mining, constructions, with autonomy stack, OS, simulation tools, and broader physical AI infrastructures. We are a 15 billion valuation company with over 1,000 engineers. We are also conducting cutting-edge research on reinforcement learning world models with applications to autonomy and robotics, with many publications in top venues, including some award-winning papers. So for the paradigm of L2++ ADAS, it has converged to imitation learning-based end-to-end with mass production. And some of the leading players also conducted post-training with open-loop reinforcement learning. To bring the safety and robustness of such autonomy into the next level, end-to-end autonomy is expected to be trained with closed-loop reinforcement learning in a world model that can reactively generate some surrounding behavior and visions in a reactive way. And this is how the paradigm is shifting for autonomy from the AV 2.0 open-loop scaling to the AV 3.0 closed-loop scaling. So at Applied, we've been creating the high-throughput reactive world model to support large-scale closed-loop reinforcement learning for end-to-end autonomy without imitation. And such kind of paradigm has achieved great performance. But the question is there a even smarter way to achieve this? So our approach is try to decouple learn to drive and learn to see. So here is how we are doing this. In phase 1, we try to learn to drive by exploiting large-scale self-play reinforcement learning. Actually, just now, Michael just gave a very good example on how self-play is empowering the autonomous racing. And I'm trying to give an example how this is empowering the autonomous urban driving. And in the second phase, we can try to utilize a super robust and generalizable self-play expert to teach another end-to-end autonomy to align its outputs of the driving behavior. So for phase 1, learn to drive, we created TerraZero, which is a self-play reinforcement learning framework that is much faster with much higher throughput than other state-of-the-art driving simulator and self-play framework. Actually, we are just utilizing some public data set scale map diversity, while it can still obtain 25 centuries of driving experience with 0 human demonstrations. And actually, we can easily scale up such kind of numbers into 2 to 3 orders of magnitude higher by scaling the GPU compute as well as the map diversity. So the policy trained from TerraZero can achieve state-of-the-art on various closed-loop planning benchmarks, which is vector-based. So it's setting a clear edge to the imitation learning-based planners, especially on the ones that is non-saturated with corner case only, such as the interplan benchmark. And it can handle various kinds of challenging driving scenarios with desirable actions, with zero-shot generalizability across the global cities. And that concludes the first phase, learn to drive. Second, let's talk about learn to see. We proposed Terra Transfer, which is training an end-to-end autonomy taught from another expert trained from self-play, which is TerraZero. What we are trying to do is to align the latent as well as the actions for both of them with the same driving cases from the offline data set. And such kind of Terra Transfer end-to-end autonomy without any imitation in its training recipe can obtain state-of-the-art driving performance on the closed-loop end-to-end driving benchmarks, setting a clear edge to the other imitation-based methods, tackling various kinds of intentionally created challenging driving scenarios with surprisingly robust driving behavior. So that concludes the talk, and the key takeaway is the autonomy paradigm has been shifting towards the closed-loop scaling, which is AV 3.0, and both the end-to-end and vector-based planner can achieve the state-of-the-art with like self-play or closed reinforcement learning only training recipe without imitation. And actually the self-play or closed RL with reactive world model, that is not just some post-training technique. Actually, they are very powerful pre-training techniques for autonomy development. And the throughput for reinforcement learning framework and the world models can be a decisive factor for such kind of paradigm for closed-loop scaling. Thank you very much for your attention.
Thanks, Wei, for the wonderful talk. You might know, I certainly do, that we're running a little bit behind on time. So we're going to reduce the time for the panel only slightly, because we don't want to cut out the good stuff. The good news is my superpower is I talk really, really fast. And you'll see I start a sentence really fast, and then I was like, no, Guru, you got to slow down. So we'll see. Today I won't arrest myself. I'll go really fast.
Screwing up the order.
OK, this is an incredible group. I was going to start, as you know, with a question around what's your definition of world model. We will not do that, because that's the next 20 minutes of individual definitions. Maybe if we have time at the end, we'll come back to that for a set. But I figured we'd just dig right in into some of the meatier topics. I listened to all of the chats today, and I picked out a few where I figured there might be some, perhaps not disagreement, but slightly different stances. So I figured we'll just have a discussion. This is not one of those, here's the question, let's go down the path. I can't stand that, God. So let's start with physics. Anastasis, in your chat, your thesis was just by generating video, you can generate inside the model an inherent understanding of physics, and you showed us some videos. Why do you believe that? And then as you think through that, I'd love for anyone else on the panel who's got a contra view to weigh in as well.
Yeah, so I think that's mainly an empirical conclusion from just scaling those models and measuring how well they perform on different physics-related tasks. In general, our approach has been, if you want to introduce inductive biases to make sure that the model learns something well, introduce those inductive biases in the data that you're training on. Don't introduce them in the architecture. So we have very intentionally, tried to learn everything directly from pixels and not introduce any kind of 3D-based priors. And we've seen that work pretty well. Like at some level of scale, you get pretty good geometric consistency. That's something you can also measure quite well. And so I don't think there is a fundamental reason in my mind why that won't continue scaling.
Someone has to take the other side of this. Is it true? Like just generate video and you get spatial knowledge inside suddenly a model and becomes a world model?
So I know that, Guru, you said you don't want definitions of world model. Let me still have one, and then I can ground the discussion. So for my definition, it is a model that predicts the next sensory state, conditional actions. Now, I think video is convenient. In fact, video is one of the sensors. It's called an RGB camera. But on a robotic system, you can have more than one RGB camera. And in fact, you have a lot more sensors. And I would say there are many modalities missing in today's discussion on world models. In addition to videos, there's tactile, there's force, there are the invisibles that we also need to put into these models to have a really holistic simulation, right? Holistic capture of how the dynamics should evolve. So I would say video is convenient. Video is easy to scale. It's readily abundant, but that's not the full story.
Okay. Sergey, you've done so many robots now that are actually in deployment. One of the few folks here who's closed the loop, along with Jim, on exactly what's happening in real life. What's your view?
I guess what I would say is that if you generate videos that people find compelling, I think it's very easy to get into a situation where you get a video that looks very good to people, but doesn't actually reflect a model's ability to simulate the kind of counterfactual effects of physics that you would care about. What that means is that when you give a model a prompt, it doesn't have to produce a prediction about what will happen to a real physical system in that situation if it does something. It just has to produce a result that to you looks like a good reflection of that prompt, which means that the model gets to choose. And that choice is actually very, very important. It gets to choose how to set everything up so that it looks good to you. Whereas if you need to actually plan and act in the real world, you need to handle the actual situation you're in, the actual plan that you're making, and whatever kind of counterfactual effect you might have. So what this actually comes down to, whether the model actually understands physics or not, as Anastasios alluded to, has to do with the data, of course. It's just that the data that we would use to get really great videos is not the data that we use to get counterfactuals. If you train a model on really good driving data, and then you ask it what happens if I drive into a building, it'll probably produce the building morphing into a beautiful road, and you're driving happily down the road. And people have actually done this, and that's exactly what happens.
Right.
So I think that the answer is yes, the model can handle physics, but you have to be very careful not to let it fool you.
Right, right. And while staying on this topic of what goes inside the model, I'd love a little bit of debate on. So we constantly hear, or we're certainly hearing now, I'll start with you, Jim. The era of VLAs is over, and the future is world action models. Do you hold this view, Jim? If so, why? And then I'd love for more panelists to weigh in. Is VLA, is it WAM, is it both, or is VLA dead and it's all WAM going forward?
Absolutely, yeah. I know I talk a lot about world action models, WAMs, and VLAs. I think it depends on the level of abstraction that we work on, right? So there's the system 1 and system 2 thinking. System 1 is fast and reactive motor skills. System 2 is reasoning, right? Coding, tool calling, all of that. So I do think WAM is a very promising approach for system 1 because many of these physical common sense, right? Let's say, how do you grasp a cup it's very difficult to break down and describe every frame through language tokens. It's just quite difficult from a first principle point of view. Now, regarding System 2, I would argue that Opus, GPTs, they are actually VLAs. These models are agentic. They take actions. I would argue these are VLAs, and in fact, more people use VLAs than they use WAM today, because VLAs also serve other purposes. And that is the part where I discuss in my talk, right? Agentic scaling. I think that's going to play a big part, right? The VLAs, which are like the Opus and the GPTs of the world, they're able to understand the world through some perception and then calling tools and be able to help auto-research. So I don't see maybe one completely replacing the other, but it's really about the abstraction level that you operate on top of.
Right. Sergey?
I actually think that it's slightly the wrong question. Or, I mean, it's the right question for you to ask us, but it's maybe like slightly the wrong question for like a researcher to ask themselves, because it puts the model before the data in a way that maybe is not actually quite right. So the key to build a really good foundation model is to be able to productively ingest lots of very diverse data. And video data is one of those data sources, and it's a great data source. Now, most VLAs that are actually good, they are trained on video data, lots of video data. It's just they're trained on it in a web scale pre-training phase, which trains the understanding backbone. So I actually don't think that the right answer is to say, like, oh, is it VLA or is it video? It's how do you use the most data? And then on top of that, there's some like kind of inductive bias, but as Ilya Sutskever used to say, inductive bias is trained data in disguise. So the effect of inductive bias might be large when you're testing things at a small scale, but it dissolves away once you scale things up. So really what we should do is say, like, okay, we're going to leverage as many data sources as possible, and then be pragmatic about what kind of outputs the model has to leverage them.
Right. Yeah. Where you're, sorry, Mika, go ahead.
Yeah, maybe I can add like two points from our perspective. So the first one is, if you think about the tasks that we are working on, like racing and table tennis, I think language is actually not all that helpful. It doesn't really, you can describe how to do the skill, but there's very little information. I mean, in cognitive science, there's this classic distinction between declarative and procedural knowledge, right? So in order to ride a bike, you actually have to do it, and you have to learn the physics of it. The second one I would say is like, obviously vision I think is a great thing to condition on. At the same time, in some applications you can't. So for instance, if we are in-game and we're shipping a game to a customer and there's like 20 agents racing, we cannot render from 20 different viewpoints. There's just not enough compute, let's say, on PlayStation to do that, because most of the compute goes into rendering for the customer, like the player. And so I don't think, these are not sort of yes-no questions. They're sort of like, okay, what is the domain that you're interested in? What are you trying to solve? What's the application downstream? I will say that having large foundation models that can capture visual knowledge and language model is in many cases really, really helpful, but we also still need to distill the thing that we're actually interested in a particular moment and then maybe ship to a consumer.
No, I like that answer. It's not an either or. It really is use case dependent, and both have really sort of interesting applicability.
One more thing to add on the WAM versus VLA discussion is that generally, there's a lot of convergence that's happening towards omni models that can actually predict both visual modalities, audio modalities, text modalities. And so ultimately, it's kind of, to Sergey's point, it's all about like, what are you specializing the model during pre-training on? Are you specializing, is the data mix biased towards more low-level motion planning? Is it biased towards high-level reasoning? So it's less about it's less about WAM or VLA architecture. It's more about what are you dedicating the capacity of the model ultimately, and that tends to be the important factor.
Right. Backstage we were talking about robots and simulated data and stuff like that. Today, from what you're seeing, how much of real robot skill has to come from things like reinforcement learning in the physical world versus the digital world? And I'd love to then, this is one of those questions where I'm sure we all have a point of view. So I'd love to start with Wei and then maybe go down the line.
Yeah, definitely. So a great question. So I want to separate that into different applications. On one side, for autonomous driving, so we care more about the behavior as well as the visual modality. And for those two, it's relatively easy for us to scale that up from the real-world data and inject that into the synthetic world with a more scalable way. And for that part, right now, it's more like this. Many of the leading players for productionized, like end-to-end, like ADA system, is mainly focusing on utilizing the real-world data, while some of the synthetic data can be utilized for the post-training stage. Well, we can see the trend that large-scale synthetic data can play the key role, or a more and more important role, for making the autonomy to be more robust and safe. While on the robotics side, I think what I learned at this very point is that for tasks related to locomotion, for whole body tracking, so the reinforcement learning-based methods can be pretty useful and even dominate that. While for complex tasks like dexterous manipulation, it could be a bit hard for us to either create the high-fidelity synthetic world capturing many of the key physics attributes, or define a good reward function to really train the corresponding policy in closed loop. So at this very point, what I saw is that behavior cloning or imitation-based methods are still dominating.
Right. Let's fine-tune this question, Sergey, as we come down to you a little bit more. Let's say there are certain tasks you just have to do in that robot's embodiment, extreme precision in data collection versus simulation, egocentric data, videos, etc. What is that distribution? How much of one do you need and how much of the other? Are we still in the age where you just need to do the task over and over again 1,000,000 times? Or can you do a vast majority of the work either sort of in silico or through egocentric data, etc.? What are you seeing in real life now?
Well, I think there's two sides to that scale, to the scales there. There's the supply side and the demand side, right? And this is where I think the future is going to be very different from the present, because in the present, I would say that in robotics, we're like in the bootstrap stage, where we're trying to figure out like what would it take to get models for robots to be good enough so that they can actually be used with end-to-end learning. But we won't be in the bootstrap stage forever. Eventually, we'll be in the stage where there are as many robots deployed out there as there are vehicles on the road today. And there will be very plentiful sources of data from robots interacting with the world autonomously. And then reinforcement learning methods that can use that real-world data will be tremendously important. The other thing here is that the challenge increasingly as the imitation learning methods that you mentioned get better and better will actually be how do you bridge that last gap? How do you go from a 98% successful robotic policy to a 100% successful policy? And there, the domain gap is really important because you really want everything to line up to be absolutely ideal. So there, I think we will also need reinforcement learning in the real world. But I think that's what's coming in the future. I don't think that's the state today. Like, I think your summary is an excellent summary of the state today.
Yeah. Jim, I know you've done some experimentation on this. What are you seeing?
Yeah, Guru, I think great scientists invent, greater scientists copy. I absolutely love to copy homework from LLMs. I look at them all the time. So what are the LLM folks doing? I think they are not just creating data anymore, they're creating environments. It's all about acquiring millions and millions of coding environments and then doing RO in those environments so that we can get the mythos and the GPT souls of today. That's how they got here. Not through imitation learning, eventually through reinforcement learning. So I see robotics to do something very similar, that we need to build environments. Then what are some options for environments? Right, option number one is you run RL in the real world. I think Sergey and Pi has done exceptional work over there. Absolutely important, right? The physics, perfect, because it's directly in the real world. And then option number two is classical simulators, right? Like Isaac Sim of the world. But those simulators, the bottleneck is not the simulation speed. In fact, the simulation runs very, very fast. But it's the assets, it's the environments, it's the tasks that we used to need a lot of artists to curate. But now there are recipes called Real-to-Sim that I believe is super promising to automatically scan the world and transport the real world into a classical simulator so you can both be data-driven while also relying on a classical fast physics solver. So that's option number two. And option three, back to world model. I think one very practical use of video world model is to use that as a neural simulator. It's a data-driven, program-by-data neural simulator. Then it can take as input actions and then generate videos and sensor states, effectively using it as environment. But the thing is, it's going to run very slow, but it will have a huge amount of diversity, as much as the world model can afford. So ultimately, it's going to be reinforcement learning across these three options for robotics, using different types of compute, using different constraints. So I would love to see this as a more holistic approach.
Right. As we come up on time, I'm going to ask two sort of rapid-fire questions that I love. So first question, we'll start with you, Anastasis. The most amazing demo in robotics or world models you've seen recently, not from your company or team?
I've seen some great things internally, but yeah. One demo or one model release I really like was by, I believe it's a new startup called Induction Labs. The model is called Photon 1, and it's effectively a world model of based on screen recording, so a digital world model of sorts. And they show that you don't need, very often, like when you're training computer use models or you're post-training LLMs to do well on computer use, you're leveraging a lot of kind of your text supervision in addition to kind of directly like screen frames from UIs or screens. But they trained a model entirely on essentially a video model on just screen recordings, and they were able to show that they actually get competitive performance with Gemini on computer use, or like Gemini, one of the small Gemini models, with an order of magnitude less compute. So I found that pretty impressive.
I think that says more about the nature of work we do on a screen than anything else. Jim, something that made you go, wow.
There's actually a robot that millions of people already buy and use on a daily basis. It's called Tesla FSD. I've been driving Tesla since last year, and honestly, I was amazed by the latest versions. And it's all like rush hours. You can see, right, the policy is able to negotiate super well in super crowded lanes, almost human-like, and I would say sometimes even better than I would have driven myself. So that gives you a lot of hope, because that is one physical system solving a very important task, autonomous driving. And once you spin that physical data flywheel, you get these huge performance gains, a quantum leap compared to a couple of years ago. So that's why in my talk today, I also stressed the importance of having data collection fade into the background. The data collection cannot be intrusive. And that's why when you have egocentric data on humans, you are able to capture this dexterity without interfering with what they're doing. And that's the way that we can draw a parallel with FSD and maybe someday get there for robotics.
I love
would
the
say that's
FSD
something.
example.
Yeah.
That's a great one. Mika.
So I'm going to pick something which is not robotics itself, but general intuition. Recently released a world model really for Rocket League, which is a game where cars play soccer. It's kind of a funny game. What's amazing about that breakthrough, which I think is about 2 weeks old or so, was that this world model could render consistently 4 different player views in that world, right? So traditionally, world models are sort of like, it's me with the world, my actions in the world, and that sort of unlocks sort of a multi-agent, kind of multiplayer, potentially interaction of multiple humans in the world kind of future, which I think is actually very important, because we often think in robotics purely about the task performance, lifting a cup, screwing something. But the world is full of other agents. It's full of things, people or AIs that we'll have to interact with. And so I think I didn't actually think it's going to happen so soon. I was thinking more like 6 to 12 months out that this is going to happen. But I think that's like a major stepping stone in the right direction.
That's a great example. Sergey.
I have an example where there's kind of a moral to the story. So a while back, there was this video that kind of went viral of the Boston Dynamics humanoid Atlas doing a backflip. And it kind of went viral because it was around the same time where there was a lot of, this was around CES, so there were a lot of demos of humanoids. And people were making fun of this because it does this backflip, and it doesn't quite stick the landing, and it sort of freaks out and does this like really weird, unnatural motion, but then stays upright. And people were saying like, oh, like, Boston Dynamics is having all these problems. Look at all the Unitary robots doing these perfect backflips. But the folks that work on robots looked at this and they realized that actually the Boston Dynamics video is way more impressive because it actually doesn't fall. Like, it freaks out, something really horrible happens, and it stays upright. Then you remember, this is a 170-kilogram robot. It's way heavier, way more complex than the more lightweight Unitary robots. And I think the lesson there is that, well, besides that Boston Dynamics has great controls engineers, is that with robots, the demo is never quite what meets the eye, right? The challenge is often not the things that you see in the demo reel, it's the degree of generalization, the ability of the system to handle unfamiliar situations and failures, and also all the complexity behind it. So it's often easy to be misled by the demo and not realize what the really challenging problems there are.
Spoken truly like a person solving real-world use cases. I love it. Wei.
Yeah, I would like to echo Jim for the Tesla FSD, which is also taking over like most of my daily mileage. And actually, there is an even more impressive thing that I saw. For that company, I cannot disclose the name because I was on the R&D car of that. But that company can achieve similar kind of level performance in super crowded kind of street with a lot of like pedestrian, cyclists, or other kind of challenging situations for 1 hour without any intervention from the driver's side. While the onboard compute of that car is only 1/7 of the Tesla like hardware 4 kind of compute, and with like even simpler kind of sensor suite on the vehicle. And for the robotics side, I think one interesting thing I saw in the Acura and the CPR booth this year is a Chinese startup called Sudo, which is also trying to push the boundary for how to utilize the synthetic data. It's doing a lot of like generalizable kind of pick and place tasks with relatively zero-shot kind of thing. Just let the audiences throw arbitrary things onto the table and do that.
Right. We're almost out of time. I have to ask this one question. The answer has to be a number, so we don't have time for anything else. A big movement in LLMs was what we call the Claude Code moment, and in the sense that that was the first use case where commercial takeoff of these technologies happened. In robotics, we think of the ChatGPT moment. I want to define this next one after that, the Claude Code moment, when the first commercial use case really takes off, just rockets off. And so your assessment, we'll start this time with you, Wei. Your assessment of what year does the first true commercially viable use case just takes off in the wild? And then if you have an idea for what that use case is, just a word or two on the use case as well.
Wow, that's pretty challenging. I will just try my best to give the numbers. So my guess would be around 3 years. So one thing is that we may also expect the data modality to be somehow fulfilled. Not just for example, a lot of egocentric or third-person view kind of large-scale data, but also the necessary physics modalities that can be well-grounded and associated with that. So those kind of data accumulation will take some time, and that could be one of the gain for having such kind of capability for the robotic foundation model.
Perfect. 3 years. Sergey.
I promise I picked this number before you answered, but my answer is also 3 years.
Okay.
I picked it in advance, though, so good check. But I actually don't know the area, and I think that the key here is to have models that are sufficiently general to radically lower the barrier to exploring different applications so that the community collectively can get through as many different possibilities as possible to arrive at that solution. So I think the key there is a general model so we can explore lots of applications.
That's a great point. 3 years, 3 years. Mika.
I'm going to say 3 years too. No.
Oh, come on.
No, I'll say 2. And I think the area is going to be somewhere in an industrial area because of a semi-structured domain, possibly availability of data. Yeah. Could be warehousing, could be manufacturing, right? So I actually think that the technology is sort of there. It's more of a question of finding the right economics, data inputs, and environments where you can actually deploy, which is where I think, for instance, deploying large robots in the home in terms of safety issues is probably further out. Right. So I think these semi-structured environments where you can use tailor the use case, bring in general models, but also combine them with training on-site or training in simulation. I think that's going to be a key.
Great. 2 years to the billion-dollar moment. Jim.
Earliest 2030, and we'll have more robots than iPhones 2035, and we're going to solve all robotics, everything, personal robot, industrial robot, no later than 2040.
Amazing. Amazing. Anastasis, bring us home. Yeah. Are we going to go longer than 4 or less than 2? Those are the bounds right now.
I think there's a wide uncertainty bar when it comes to deploying robotics for household tasks. I think I agree with Michael in terms of for very narrow enterprise use cases in like things like logistics or in kind of the factory, like you're gonna see deployment within the next kind of 2 or 3 years. But when it comes to actually dealing with the complexity of like a home and being able to operate autonomously at like many nines of reliability, it's gonna, I think, probably 5 to 10 years seems more likely.
Can I give an upper bound? I think for some economies, and this is not a technical argument, but we're going to have to solve it in 10 years. So if you take large Japanese corporations, for instance, in manufacturing, any industry, 60% of the workforce is 50 years or older. And so in 10 years, they will all be gone.
So those are the bounds, 2 to 10.
We'll have to solve it by then.
All right. All of you are at the top of your domain, top of your fields. I really appreciate you spending your Saturday afternoon with us. Thank you so much for the wonderful presentations and the chat.
Hello, all. How's everyone? Was it a good break? Good break? Everybody caffeinated? Ready for some amazing insights? I hope so. We have a great group gathered here today. My name is Brad Olson. I'm the Deputy Bureau Chief at the Wall Street Journal for Technology. And I'd love to actually allow these panelists to introduce themselves. And I've asked each of them to think, kind of have a response ready for like what I call like a starter question. I think one of my favorite things to do when we talk to people in AI or in the AI race is to ask a little bit about what's a wow moment they've experienced recently, or even a moment where they might have been disappointed by the performance of an AI model or whatever their expectations were. And so I'd love to have everyone introduce themselves, and if you could answer either side of that question when you introduce yourself, if you had a recent wow moment or even some way in which maybe what you thought would work with AI didn't live up to expectations. You want to start?
Oh, sure. So, hi, everybody. I want to thank the sponsors for inviting me. My name is Jeff Wecker. I run engineering for an investment management firm called 2 Sigma. Before that, I was a partner and the first chief data officer for Goldman Sachs. And before that, I was at Bridgewater Associates and renovated their investment engine. I can keep going, but I'm an old guy, so there's a lot of before that's as well. So we'll stop there. Do you want my answer for your question
I think I'd love to. It's a nice conversation starter.
So amazing things. I'm embarrassed to say that a few years back, I tried to use one of the LLMs for parenting advice, and it was terrible. Just absolutely terrible. And I've tried it more recently, and I actually got some pretty impressive results, which I don't know if the LLMs have gotten better or I got a lot worse, but very impressive anyway.
Very cool.
Hi, I'm Jen Allam. I'm one of the co-heads for one of the AI teams at DE Shaw. And something that I found delightful recently, perhaps not revelatory in usage, is having AI be an executive coach. I hope I'm not alone in this room as being the only one with growth areas, but it's delightful. If there's something you're working on, DE Shaw is very known for precise communication, and so it's an area I want to get better at, and it's both wonderful for timely, actionable insight, qualitative and quantitative, as long as you give it the right context. And I'm getting a ton of value out of it, so I love that about it at the moment.
Wonderful.
Okay, go next. My name is Ali Nazari. I run deep learning research team at Susquehanna. Before that, I had my own startup. It was actually a deep learning hedge fund as well. And before that, I was an information theorist. I guess it's so easy to be excited about entire, evolution of AI and, machine learning AI and then, agentic systems in the past few years, particularly last year. What I want to take is actually disappointment. A few weeks ago, maybe a month ago, I was trying to work on a research problem. I asked one of these frontier AI models to help me think about it, and it came up with something super exciting, super amazing. Came up with about 30 different plausible solutions each of those ideas. If I wanted to do myself, it would probably take me months, if not quarters. Then I realized actually the hardest part didn't disappear, it just moved. Now I found myself, instead of just trying to come up with idea to generate idea, I was trying to figure out which of these ideas that gave me worth my time. And that's the reminder to me that, I mean, all of these, like, you know, bottlenecks, all of these challenges, they don't just disappear, they just move.
Yeah, my name is Li Deng. I spent about 18 years at Microsoft, and then I joined Citadel, and now currently with Vedic Investment. So before Microsoft, I was academia. At that time, I started doing neural network, right? It just never worked, right? And even the first 10 years at Microsoft, I turned everything, all my machine learning tools into Bayesian network, you know, deep generative model, you know, but not that by neural network, but by, you know, the standard statistical method. And the result is just slow. You know, I work on voice recognition and translation, spoken language processing. And the wow moment for me, it started in 2010 when I first got the opportunity to look at a neural network. Actually, it was inspired by Jeffrey Hinton. Later on, he got Nobel Prize. And the first 2 or 3 experiments that we tried already just shoot down the error rate by about 1/3 to 1/2. And I immediately say, throw out all other tools, just embrace neural network, deep neural network. We built very, at that time, up to about 13, 14 layers in as early as 2010. I was reminiscing with Jennifer earlier today. At that time, you know, most of the people at Microsoft wouldn't believe that it's what. That was my big wow point. And then the second wow moment for me was when ChatGPT came out. The first time I was trying ChatGPT about 3 years ago, I just thought that something must go wrong. That's exactly what many people said during my speech recognition time at Microsoft. They said, oh, you probably mixed training and test data, right? Now for ChatGPT, we actually were able to use that, you know, as the product. So nothing could be wrong, right? Because it's the real testing. And then it took me, I have to get back. At that time, I was already in Wall Street there. I have to get my previous a team member who used to report to me. He actually at the time was leading the reasoning team at Google. And he had to explain to me that there are certain kind of decoding technique that is different than the traditional machine learning. And then that made me immediately realize that, wow, that's real. But now, when Agentic AI came out, there was small amount of wow moment. It actually not just, you know, do pattern, you know, recognition, pattern matching, you know, the kind of traditional machine learning task, but it actually can do the reasoning, but also it can also kind of put things together. It actually does knowledge kind of management, and that part really wowed me. Okay, I'll stop right here.
I think we've all had that experience where there are a series of those moments for all of us. One of the things that I wanted to ask, because I imagine many of you are here today to hear from, you know, people in finance and Wall Street. I'm interested in maybe what the differences might be. You know, a lot of people might be familiar with AI in the context of software engineering and the capabilities that are possible, you know, to accelerate software engineering. But I wonder if any of you could address the adoption curve within finance. What are different things that are in consideration, you know, as opposed to in a technology institution or organization? What are different kinds of things that are being looked at or that are important?
So I'm happy to start and then turn it over to my colleagues. We are mostly at Two Sigma, a technology firm that invests. Of the 1,800 employees that we have, about just under 1,000 are in engineering, another 400 or 500 are modeling, and then all the rest of the firm, the rest do everything else. And so for most engineers, you give them a new tool, and it's hard to believe. You think about Claude being available in February of 25. We started using it within a few weeks and went GA within a month, 6 weeks. And so engineers, you see different rates of adoption, but you see engineers ready to take another tool in the toolbox, look at it, and say, oh, I know how to build with it, and start going. What's exciting to me is the potential to have everybody at the firm think of themselves as AI first. And there are different rates of adoption, and it's becoming very clear as we look at various metrics that those that adopt sooner, faster, are clearly becoming much more productive by a lot of different measures that you look at, code branches or work, things they've written, things they publish. And so our goal is to try to figure out what is the right set of tools, what's the right partnership for everyone at the firm to be AI first. And while a lot of our focus at the firm is on the investment pipeline, of course, there's every single other workflow at the firm that can lend itself to that. We're seeing people now that have no technical backgrounds starting to use Claude in auto mode or one of our in-house workbenches in auto mode, and it's really impressive to see people experiment. And I think as a result, the rate of innovation now is as high as it's been in recent memory.
Fascinating.
I guess I can add something to that. I mean, the adoption is real. I mean, in quantitative finance, Susquehanna particularly, all engineers, researchers are using AI tools. I mean, as Jeff mentioned, there are different rate. Some people use it more, some people use it less. But I mean, one thing that is different in finance compared to a software company is that the cost of mistakes. So in a software company, if your AI model make a mistake, I mean, hopefully you have unit tests, you're going to figure it out, you're going to fix it, and you move on. In finance and many other fields, it can cost a lot. It can cost money. It can be kind of even a lot of other dangerous thing to the entire kind of society in some cases. So we need to be, in general, quantitative finance has been early adopter of many things, whether it's statistical learning, whether it's machine learning, different type of thing. But when it comes to agentic system, I mean, we need to be careful. And then, I would say that trust is something that needs to be gained. There are some things that I definitely use AI all the time for, and there are some stuff that I prefer, human be part of it. And then the other thing is that I think trust needs to be regained. Model change, data change, market shift, everything happens. And then something that you were trusting 6 months ago might not be trustable right now. So I think it's all about the mistake and then the trust to the model.
Jen, maybe one thing I'd like to get your insight on is how do you encourage teams to experiment with and evaluate kind of new AI tools before deciding what to scale?
I think an underappreciated quality of firms like ours is that in many ways they operate like innovation businesses. There's a relentless need to be able to innovate on what you do. And that means the DNA is there for experimentation and history is there for experimentation. D. Shore is perhaps known as one of the original kind of quant funds. Of course, AI is in the DNA. And as a federated business with multiple strategies, we're able to unlock experiments across the organization and allow for a bottoms-up finding of where the value is. So we think about the rate of learning and the rate of discovery we have, let lots of experiments run, be maximalist in the policy, build and buy and everything in between, and then see what catches fire. And then think about where we scale that and for who and how. So it's a continuous process that is very much part of the DNA and that this new advent of AI is accelerating.
Leah, I'd love to know in your organization, how are you balancing the experimentation versus cost problem that a lot of companies are facing right now?
Oh, yeah, very much so. So compared with the high-tech world, the quant world has a similar kind of workflow. Right? You extract features, that's what we call alpha, and then you have a model to do the forecast, just like prediction, pattern recognition. And then you do experimentation and evaluation we call the back testing, whereas in high-tech world, you call the validation. And then you go on testing in the high-tech world. Now we call the paper trading or online trading. Now the key issue here is that the signals are extremely noisy. The input signal is noisy. The output signal is even more noisy. So one of the reasons I actually decided to move from Microsoft to the Wall Street is I tried to understand exactly. I thought that the problem is going to be unsupervised because the signal is so noisy. You might as well just forget about the signal. It turned out that it's a mix. If you're purely using unsupervised learning, you're not going to go anywhere. And then you do have a little bit of supervision, but it's extremely noisy. The first time I look at the data, finance data, that's after residualizing all the returns, I thought that I got the wrong data. Right? It's just random noise or random walk, almost everything there. But it turned out that the signal is right. You want to extract a very tiny bit of signal from there. So we need to use a special kind of technique, especially in the experimentation and evaluation side. So earlier on, we heard Google DeepMind, Oriol Vignal, he went through a recursive, a self-improvement pipeline, all these pipelines. We went through them all. But we emphasized a lot more on the evaluation side. And then because evaluation output is very, very noisy, you don't even know what will be the right signal to predict. And then how do you provide the right feedback in order to further improve your features, etc. So we put a lot of effort on that. But so the key over the past few years of the work on applying AI, it's not as much as making the model bigger. You expect to have emergent capability coming out, just like large language model. We try quite a bit, but we don't know how far we are going to do. But my hunch is that we need to go much more further away because of the nature of the noisy input-output, right? So we actually gave up on that part. And then the key focus would be, to your point, how to make the entire system to form a right self-loop in such a way that, actually agentic method is really the key that minimize, all the human effort, engineers' effort, alpha engineers' effort to put them in place. And that's the kind of focus we have been put on in my current work.
But if I could just add something to the point about cost, because I think it's going to play a growing role going forward. If I think about historically our business, when it was founded 26 years ago, most of our modeling was fairly low dimensionality, statistical models, and then sort of low to mid machine learning models, and we moved from that to ensembles, and we started to train our own transformers. Then you had, with GPT 3.5 coming out, you finally had the ability to use publicly available models, because the frontier firms gave you such a head start in training that reduced the cost of doing that. I think what we're seeing now with the advent of agent-centric workflows, we are on the eve of the potentially an explosive use of compute demand that we have to be pretty careful of. Because if we have, if I use the 2 Sigma example, we have 1,800 employees today, but if behind those 1,800 employees there are 250,000 agents doing operation, all making their own compute demand, then we really have to think about the implications, return on investment of that. Now, to be fair, when you're seeking alpha, you dig a lot of dry wells. There's no doubt about it. But at some point, you have to look at the maturity model of the investments that you're making in identifying alpha opportunities, and then think through whether or not you're failing fast enough to protect against the massive investment demand that you have in compute.
Interesting. I think maybe to switch gears there, because you mentioned the personnel, one thing that is a great question for all organizations is like how the AI age has changed kind of the search for talent, the recruiting process. And would love to hear from everyone about that and kind of how different things that you look for has changed in this age and in this era. Obviously, most people are looking for people of talent, but how do you find them? How do you sense that someone has experimentation capability and maybe the skills to make a lot out of those things.
I think, yeah.
We think about AI as an opportunity creator, something that is helping us innovate and drive higher quality work. And so we are deep in finding great talent continuously. And DE Shaw, I think, is known in some ways for hiring particular types of people and looks for curiosity, lifelong learners, critical thinkers, systems thinkers. These are qualities that are becoming even more important now. And when people commit to the firm and have decades-long careers, as is common, then actually you're looking for a degree of adaptability, that they will have multiple careers within the organization. And so as I'm building out a team and I'm thinking about how to hire, it's kind of emphasizing those qualities more alongside functional expertise, and then building on that, thinking ahead to what's the next role and the role after that they'll be doing with us.
Yeah, I completely agree. And then I think some of the qualities still is going to stay the same. So we want smart people like that who are curious, who are asking like right question, who can work independently. And then these qualities matters actually maybe more than before. One thing that changed though is that the interview process, the type of thing that we were questioning people before, was built for a time that implementation was the hardest part. Now that AI does good amount of implementation for us, the type of things that we care about change as well. We need to make sure that people can adapt to this kind of thing, they can use the tools properly, and they can detect if an AI system, confidently wrong about something, they should be able to detect it. One thing I'm actually wondering is that the next generation, how they're gonna develop judgment. If you think about judgment, traditionally what we were doing is that we try something, we make a mistake, we learn from that mistake, and then how judgment is being developed. Now that AI does most of the experimentation for us, the question is that how that judgment is going to be developed. And this is the question, I guess, for next generation.
Yeah, so in my firm, for example, maybe just 2 years ago, right? Most of the team members are, PhDs from, Ivy League, from mathematics, from physics, some computer science, Nowadays, I think 2/3 of them are no longer with the firm. Before, sometime every now and then we get the CV, coming from, universities. They don't even have PhD. We don't even look at the CV to say, sorry, we don't hire, non-PhD. But now we have maybe more than half of the people who are not, who are not even PhD. For the intern, we actually enjoy undergraduate students, senior undergraduate students to come. They actually can do agentic work, probably faster than full-time the people there. So all the talents actually profile changed quite a bit just over the past 2 years.
Yeah, if I could just clear something up, we are hiring. We are hiring, and but I do think what people are doing is very different. We've eliminated coding tests, of course, because we'd be testing LLMs and not people. Yeah. But I do think that the kind of scientist, the kind of computer scientist, the kind of engineer is going to be even more important to us going forward. Their ability to take a problem, decompose problems clearly into components. Can they actually prompt to get the kinds of outcomes that we really want to see? Can they design agents that are able to use judgment and really help to accelerate either the generation of features, the generation of models, the generation of order placement or portfolio construction models. That's going to be critical. And so we're looking for people that have the cognitive depth to be inquisitive and learn our business, and then bring to bear the skills that they've learned in their various scientific backgrounds to apply them to deconstruct the ideas that they may have about what's possible in the future, and then deliver outcomes.
Well, I think it's certainly good for everyone in this room to know that people are hiring, that it's possible out there. I think another thing that I'd like to ask that I think is relevant to the talent question, for those of you who are willing to answer, is if you were going to design a quant firm from scratch, what might be different about it now, in this age? What might you do differently than maybe the existing systems and infrastructure that you've seen?
So I think one thing that I would do is that I think quantitative trading has two parts. One is the research side, the other one is trading. One side is creating the knowledge, the other side is using the knowledge. So, if I want to build new quantitative trading firms, I basically focus more and more on the research side. And there are a couple of things I'm going to do on research side. The first thing I'm going to do, make sure that every single experiment, the failures, the successes, everything that has been done is become part of a knowledge of the organization. I guess there are things that, especially the failures, many people put them in their mind, and then when they leave the company, the knowledge goes with them. The second thing I would do is that making sure that, the evaluation become part of the research loop, not something that we add at the end. And the third thing I'm going to do essentially is going to be making sure that researchers, the human research and AI researchers, go to the same kind of research process. They're going to be evaluated the same way, regardless of whether is AI generated or human generated. And then the knowledge we're going to learn from both of them is going to go to the knowledge of the entire organization. I look at research as not a collection of tasks. It's a process of continuous learning. And I think that's the big distinction.
While we build a fair amount at DShaw, we also partner widely with companies outside and like to be a good partner in terms of collaboration, especially when you think about kind of enterprise readiness for what it takes to be able to deliver a product in a regulated space where we care about security and care about our IP deeply. And when we look at products, I think to Ali's point about the kind of know-how the organizations already have, both technically and knowledge-wise, I think there is an opportunity for even sharper thinking about the value proposition of new products in this space, about what they would be, how they would be additive to companies like these.
Well, I have a bit of a wild card question. I want to see if people are up for answering, but I think I'd love to hear what so many people think about this question. If you're not up for answering, we can go to another one. But I'd love to know if anyone wants to weigh in. What is one widely held belief about AI that you think is wrong?
I think the idea that you need fewer people. Certainly there are roles and jobs that are not going to exist in the future. But the idea that you don't need technologists, scientists, mathematicians in a world where more systemic decision support is going to be the future, I think it will turn out to be false. Now, I believe what will happen as a result is a whole host of new roles are going to be generated to take up the changes that are going on in the workforce. But I do believe that one of the ideas that are being advocated is that there won't be opportunities for people in the future. It just doesn't make a lot of sense. It hasn't been true with any other major invention over human history. The world's changed, the markets grow, and the opportunity for more people to make an impact continues to grow.
Does anyone else want to try that one?
I guess I can.
Yeah,
go ahead. Go ahead.
Yeah. So we heard earlier several talks in robotics and also in foundational model, right? People still talk about, one wave of scaling and the second wave of scaling. There could be third wave of scaling. So I personally feel that maybe it could, I think for robotics, it could be true. Whereas in finance, I just don't believe this is going to be correct. We have done a lot of work over the past few years trying to scale. We never reached the point where we have the emergent capability come up. But I think in finance, the most important part really is the systematic way of looking at the full system, right? Especially the integration between different components of machine learning, especially at the output side, evaluation and the feedback. Because feedback in the financial market is a very, very different type of problem than in the high tech. and that part of design probably carries a lot more weight in the agentic area. And I remember when I moved from Microsoft to Citadel 7 years ago, my big boss, very wealthy, billionaire, right? He actually first personally told me that we hire you. We know that you disrupt the speech recognition, you practically solve a speech recognition problem, and then you do natural. We hire you. It's not. We don't expect you to bring that kind of expertise to Citadel, because if you build a system for translation system, for recognition system, it may work today, and then more likely next week you don't have to adapt. Right? Maybe, when you wait for 3 or 4 years, when you have different president, for example, the language change, right? And then you have one president, different policy, different, and then language model change that will affect speech recognition. At that time, you have to adapt. And maybe for voice, you have to wait maybe a few years when coding standard changes. Maybe whatever system that you trained before may break. If you want to bring that kind of system into finance world, you're going to fail, because in financial market, every time you put order into the market, people react that differently. It changes the environment much more so than the high-tech world. I think this is the drastic difference between different worlds. So I think a traditional way of thinking in high-tech world of scaling and then doing all sorts of things that you heard here, maybe most of them may not be applicable to us.
Well, thank you all for joining, and thank you for hearing and listening to us. I think that concludes our panel today. And yeah, thanks everyone for listening.
Thank you. Thank you.
And it's my pleasure now to just introduce the next speakers. We'll be hearing, there's a fireside chat, and we'll be able to hear from Andrew Ng, the co-founder of Google Brain. And anyway, it's silly for me to introduce these people. They have so many titles, but he's a co-founder of Coursera. He actually coined the term agentic relative to agentic AI, so that's pretty interesting. And also is a founder of Deep Learning AI. And then also he'll be speaking to Alfred Lin, the general partner at Sequoia Capital. Thank you.
Andrew, I think you and I are the last ones, so we better be entertaining.
Counting on you for that.
All right, we'll start with heavy-hitting questions. You said in February that AGI is about 50 years away.
Oh, I see.
Still believe that, given how fast things are moving?
I think depending on how you define AGI, we might have gotten to AGI either 30 years ago, or I think quite possibly not yet for many decades. The definition I know is AI that could do any intellectual task a human can, and that means AI that could take 5 years and write a novel PhD thesis, or maybe faster, or AI that any of us with a few hours of practice could learn to drive a truck through a forest, so AGI seems to me like it would have to do that too. But because of incentives between a Microsoft and an OpenAI contract, which has changed, so that's just gone away, there was a specific financial incentive to lower the bar for AGI to make it easier to get there. And there was this definition of AI that could do 50% of all economically useful work. But if only we had put in place that definition 100 years ago, then as most of the work transitioned from agriculture to non-agriculture work, then I would declare we got to AGI like 30 years ago or 50 years ago or something. So depending on how you define it, I think the original definition is still many decades away. But I think because the agreement between Microsoft and OpenAI, I think that there's now less hype about AGI, which I think is a good thing.
All right, another hard-hitting question. A lot of controversy about open models. A lot of talk in Silicon Valley, a lot of talk in Washington, a lot of people posting about open models. In fact, Jensen's first tweet, he's never sent out an X post ever before. His first X post was about open models. and defending it. What do you think of open models? Why do you think we need it? What's the concerns around security? Are those things valid?
You know, over the last 3 years, 3 years ago, I was surprised at the intensity of the attack on open weight models. I think many of you have already seen, right? If someone spent billions of dollars training a model, it's kind of inconvenient if someone else releases an open weight version that degrades the value of that investment. So kind of 2, 3 years ago, I was in the room when a number of executives from a number of companies, kind of the obvious ones, were saying to government regulators, frankly, misleading, hyperbolic things about AI safety in order to try to drive regulatory capture. I think I'm actually very glad that a little bit later, because of the work that a lot of the open source community did, flying to DC, speaking with Congress, speaking with the White House, that at this moment in time, there is broad awareness in Washington, DC about the regulatory capture moves. And I think, but at the same time, I was actually really happy that Jensen put out that statement. Really well written, worth reading if you've not yet read his statement on why open weight models are an important thing. And right now, my read is the battle for the sentiment of open weight models is won on social media, but it is not yet won in Washington, DC, and in our state houses, so we cannot yet relent on our defense on open weight models. From what I'm seeing, I think open weight models seem safer to me than closed weight models. In fact, just last week, I had my own example of the OpenAI hacking Hugging Face and Hugging Face needing an open weight model to defend Hugging Face. So my team was doing security review of an open source agent harness that my friend Rohit Prasad and I have released called Open Worker. And both Fable 5 and 5.6 Sol refuse beyond a certain point. And we actually used GM 5.2 and QEMU K3 in order to complete our own security review. To be clear, I hope Anthropic and OpenAI succeed. I like both companies. I might be the only person in the world that both Sam and Dario has worked for. So I really hope these businesses succeed. At the same time, I hope we find a path to all of my friends in these companies doing well and also having a wonderful, fantastic open way, open source ecosystem, because that ensures that there are no, I don't want there to be gatekeepers to AI.
Yeah.
Thank you.
I couldn't agree more. And also, since everything costs so much, why pay for more to OpenAI and Anthropic if you can actually train something yourself? You're going to do that for certain things because you need the latest intelligence, and you're going to want certain other things to be trained yourself. So.
And remember, I think Sequoia actually came out in favor of open source, and you're actually ahead of many other VCs. I really respected that.
I think the history of venture capital is to try to find things that are cheaper, and open source is a form. Open source. Let's move all the way back to open source and not open weight, because I think it's clarifying to study business history. A lot of the products that were developed on the internet were built on open source, and if the open source software was not available, a lot of things would cost a lot more and take a lot longer to build. And only certain companies would be able to sort of build that type of infrastructure. Open source is the reason why there's so much diversity of databases, so much diversity of browsers, so many diversity of many, many things that we do. And open source for a startup, for software, was a form of distribution. And was a cheap way to show how smart you are, how capable you are, how you're able to build something and give it to the world to use, and then let other developers develop with you. It was a form of recruiting. These things were controlled by large companies for a period of time. And so I think open weight models have a place, closed models have a place, open models have a place. And the knock on open has always been it's not as safe. That was true with security for software, open source software as well. Yes, you have to patch those holes if you're going to use them. But it is a very fast way for you to get up and running. Some other sort of hard-hitting questions. You said recently that there's bubble risk in the model layer?
There's what?
Bubble risk in the model layer? asking. I'm asking for a friend, in the investment community. Should we be worried?
Yeah. Now, I think the other side, I don't know, Alfred likes doing this hard-hitting stuff, I don't know why. I think the part of the statement that I was more confident in was demand for inference. I think there's no practical ceiling, and so as much capital is going into building data centers, if we build the data centers, we will use up, I think, all the inference capacity we can build for quite some time. Doesn't mean no one will lose money. Maybe we'll overbuild, but that risk seems lower. And the model layer, has been the kind of intelligence per dollar invested is a tough equation, right? The capital going in is growing, very quickly. The intelligence is maybe also growing very quickly. So where that plays out, I don't know. I'm cautiously optimistic there isn't a bubble, but I think I wish I could rule it out. But I'm actually less worried about. I think we clearly need a lot more data center build-outs for inference, because even take AI agentic coding, I think penetration is very low, but all of us that use AI coding agents see so much, speed and efficiency gain. So I'm very confident that AI coding, just as one example, will have vastly greater penetration in the future and drive vastly greater demand for tokens than there is now.
So we're at the Agentic AI Summit. So what kind of agents are you building? Coding agents is like, what's potentially as big as a coding agent in the future?
I don't know. I wish I knew. Yeah, maybe I want to share one perspective. One thing I think a lot about is, so it turns out that where AI is creating value, with the rise of the internet, there was the horizontal information search layer where Google, maybe Bing won that. And then there are a lot of verticals, right, with the rise of the internet. So kind of Uber and Lyft fought out for ride sharing, Travelocity, Expedia, fought out for travel, there's retail, and so on. I think what's happened is for the horizontal information discovery layer, ChatGPT and Gemini seem to have the leading position, pretty hard to displace. And then for the vertical applications, the bucket that's the single most valuable so far seems to be AI coding, where coding agents have kind of been incredible. I feel like my team uses a lot of coding agents for data science work as well. I spend some time in the financial sector. So we do some work with some large banks. And I find there are a lot of agentic workflows that are useful for financial services as well. But it feels like there are, I don't know, I wish I knew. I know Alfred's actually spent a lot of time thinking about what are the new categories that may emerge, right? Not just what we could do a bit better, but the brand new creations. You'll say that.
Yeah, if I knew, I would start a company. It's maybe the best time ever to start a company. We often talk about at Sequoia that in technology there's accelerating change. And there's two parts to accelerating change that is very difficult. One of which is what we're talking about today, we didn't talk about 3 months ago. Which means that in 3 months, whatever we're talking about today, we won't be talking about in the future. And if you're building a company, which is even more important than if you're like me, who's investing in people who are building a company, you really need to be able to build something that lasts over a longer period of time. Today, given the amount of capital that is needed with compute, you're going to be raising a substantial amount of money, and you want it to last for a decade. It's very, very hard to sort of understand what's going to last for a decade. But I can tell you that one of the things that I think people often confuse is the immediate thing that seems obvious. Those things are going to get done by even some of you in the audience, but it's also going to be done by large companies. And I use the analogy of mobile. Everything that was on the internet made it to mobile. Mobile apps were a little bit complicated, but it wasn't that hard to take the internet and make it mobile web or mobile app. And then I look at this device, what is it different from the last device that you had, which is a laptop? This thing is always on. So for communications, all the apps around communications blew up. Even email blew up or texting blew up, but you have to find something unique and non-obvious. So even though there are lots of messaging services, WhatsApp was different because it was about long-distance SMS, which is solving a cost problem. SMS inside this country, we all pay one data plan. It wasn't that big of a deal. But if you're sending international SMS, that's very, very expensive. So international SMS, WhatsApp solved that, and that became a big company. And this device had two things that your laptop doesn't have, one of which is the camera, so everybody became a photojournalist, so you can invest in that area. And the other thing was GPS. Everybody had GPS on their phone at some point, and that was not true from the previous generation. And so often when I hear about companies that are taking existing context and processes and feeding it into AI, I'm like, that's obviously going to get done. But the sort of what is uniquely going to be made differently in AI, I think we haven't pushed the boundaries of that. And I'm looking for that.
Maybe I'll share one other thing. I think that a lot of people think about what are the new modes in software. I think it's actually a very valid question. And I find that there are a lot of stuff that can be built, and if it's valuable, let's actually build it. But if whatever you build can be replicated by anyone with a coding agent in 3 months, then the traditional way of running SaaS businesses, where you build software and sell similar software for a long time, seems like that might have to change. So I think that the analysis of modes of what are the deep tech things that are genuinely hard to replicate and that are going to be valuable for long term. And also, I'm actually seeing some businesses where, frankly, the frontier labs have done this. You build stuff that goes obsolete in 3 to 6 months, but you keep on having new stuff that keeps on getting obsolete, but you accumulate some assets along the way. So keep on building something that keeps on going obsolete, but everything that quickly goes obsolete helps you accumulate some asset before it goes obsolete. So the asset you end up accumulating over time grows into hopefully a more defensible mode. So I think these new patterns of building businesses, are quite interesting.
We talked about the bubble thing. Jobs, AI jobs. No AI job apocalypse? You've said that a few times.
Yes.
I agree with you. So why do you think that?
Yeah, so this idea that AI will put 50% of people out of a job, they'll be rioting in the streets or whatever, this is false. There will be no AI job apocalypse. Part of the regulatory capture fear narratives of businesses was this, my technology is dangerous. No, mine is even more dangerous. No, regulate me harder. It's just kind of, and I think I feel like Wall Street Journal just reported a few days ago that even some large businesses that thought AI would reduce labor is actually turning around and starting to hire more. And if you look at the job most affected by AI, it is actually software engineering because of coding agents. So much acceleration and automation. The software engineering job market is very healthy, and frankly, we just can't find enough skilled AI engineers. I believe that as AI starts to enter other sectors as well, be it finance, marketing, HR, administrative jobs, and so on, that we'll see a similar pattern of very rarely job collapse, but people actually end up being busier. And what we've seen in software engineering is if you take, say, a back-end developer and they start using a coding agent, then it frees up, some of their time, 30, 40, 50%, I'm not sure. But that remaining work that they do, which is a complement to the coding, therefore becomes even more valuable. And if we free up some of their time, then say front-end or back-end developers end up rising and taking on a broader scope, which is why these days I don't hire front-end or back-end or whatever developers. Almost all of my engineers are full-stack developers. We can now all do that. I'm seeing early signs of this in other job roles as well, where previously maybe you had a marketing coordinator that did one role, driving the coordination marketing campaigns. But if AI frees up 30, 40% of the time, that marketing coordinator can rise up and become more of a full cycle marketer and run marketing campaigns from start to finish, do the data analysis, drive growth. And so I think this pattern will repeat in other industries, in other job categories as well. And the number of jobs where AI could do 100% of the time, 100% of the tasks, thus causing a collapse of that job category will be very small. What this means is one of the challenges ahead of us is when someone comes and does, one thing, I think all of us use AI agents a lot in this room, maybe. I don't feel any more, I feel like I'm even busier than I ever was, right? And because when AI does some of our job, the complement becomes even more valuable. But the challenge for a lot of job roles will be upskilling, so that if 30% of your job goes away, how do you rise up and do that broader set of tasks and also learn to use AI. And so that's why I think I also still spend a lot of time at Coursera and Udemy and DeepLearning.ai and LearnVector, which we just announced this week, to try to address that training upskilling.
Yeah, I fully agree with you, Andrew. And I think the one thing that people misunderstand, we sit in an academic institution here. In academic institution, you solve one problem and it creates, every problem has a solution. That's part of the sort of thesis in academia, and every solution creates more problems. And I don't think we're going to run out of problems. And maybe the exact thing that you're doing today is going to get automated, but if we lived 200 years ago, 80% of us would be working on our farm to make sure that we can feed ourselves. It's kind of good that we can automate a lot of that so that we can do other things. And so I fully agree that maybe a software engineer will not be coding, but as the last panel said, your ability to break down problems, large problems into smaller and smaller problems is still going to be important. Your ability to figure out which problems to solve is still going to be important. And those are not going away.
Yeah, in fact, in terms of what's not going away, I think sometimes people say, I feel like the jobpocalypse messaging has made a lot of people nervous about jobs unnecessarily. And I feel like it turns out in our surveys of, excuse me, a lot of software professionals, people are actually confused about where to go and what to learn, and worried about learning something that will go obsolete in 3 months. So I spent a lot of my time thinking through what exactly are the skills that being skilled at AI engineering or being skilled at these other things, what that will require and help people to get there. And that feels important. I know here in Silicon Valley, there's a ton of work on accelerating AI development. Fully support that. Let's keep working on that. I think the complement of that has had insufficient attention, which is why I would like to also spend more time on accelerating not just AI development, but on accelerating human development. So that too seems important to me.
So maybe following up on that, you were a PhD student here 20 years ago. Is that right, approximately?
Boy, was that long? Yeah, something
at all.
Yeah.
So you've had a fabulous career after graduating. You're a researcher, you're an academic, you're a builder, you're a founder, you're an investor. You were at the forefront of AI while you were at Google Brain. What would you advise people in the audience to do in this kind of day and age?
Actually, I think of all my credentials, you left one out that I'm probably most proud of, which is father. That's really precious.
Father is actually pretty fun too, yes.
Thank you. Thank you. This sounds cliche, but this sounds like the best time ever to build. I find that my teams, we see so many opportunities, and yes, we can code faster now because of coding agents, but somehow all of our appetite, our list of ideas seems to grow even faster than we can deploy coding agents to keep up with us. One thing that I found interesting was, for a long time, my team, in addition to hiring people with strong technical skills, strong AI skills and all that, we tend to look for people with a high degree of agency, meaning people that don't wait to be told what to do, but will look around, see what's going on in your company or in your context or in your academic university or whatever, and have high agency to just decide, I'm going to do this, do it in a safe and responsible way, don't harm others, but really don't ask, if there's some things you don't need permission to do, so long as you don't harm others, just go do it and prove it out. Or go do it, and if it fails in a way that doesn't harm anyone, that's fine too. The thing that I found really interesting was we're actually seeing in more and more job descriptions, companies looking for people with a high sense of agency. Oh, and the weird way of saying this is I see companies looking for people that are highly agentic.
How do you screen for someone who's has high agency or highly agentic?
I think one of the ways to do it is actually behavioral interviewing. We'll ask people what they're doing, and if someone says, well, the last 5 years I did what my boss told me, that's one type of person. But then there are people that say, you know what, in my spare time I did this, on the weekend I did this, and this failed, oh, but that thing worked. And I tried this, it didn't work, but that worked. There are a lot of people that I mean, frankly, I think it's also so much fun. So, I don't know, last night I was running Codex and Cloud Code in parallel with the same prompt to wake up this morning to see which one did better. And then actually in the car ride over here, I started another. Again, it's just, I do this stuff because it's fun, right? And I think sometimes I build something that ends up being useful to other people too, and that's very satisfying. And a lot of the time, I build stuff that's totally useless and they will never see the light of day. But that also, the many very inexpensive failures is also a really fun thing to do. So long as you can do it in a responsible way that doesn't risk anyone.
Well, that's all the questions I have. Thank you very much, Andrew. Appreciate it.
Thanks, Alfred.
Thanks, sir.